Welcome to our workshop on elemental and structural analysis in SEM with energy dispersive and wavelength dispersive X-ray spectroscopy, as well as electron backscatter diffraction or EBSD. My name is Tirza Abbott, and I am the manager of the Scanning Electron Microscopy Facility here at the Nuance Center at Northwestern University. And we are very excited to be hosting today's workshop in collaboration with our friends at Oxford Instruments Nanoanalysis. This is a 2-day workshop, and today we'll focus on EDS and WDS. Tomorrow we'll focus on EBSD, and we hope you enjoy the morning talks given by our fabulous invited speakers. These talks will be recorded, so if you want to watch them later, they will be on the Nuance YouTube channel after the workshop. If you have questions for our speakers, there will be a short Q&A after each talk, so please type your questions in the Q&A window in Zoom. There's a little Q&A button at the bottom of your screen, and our speakers will answer as many questions as time allows, and you can follow up with them after if necessary. So with that, it is my great privilege to introduce our first speaker of the day, Dr. Jennifer Mitchell. Jennifer received her PhD in planetary science at Monash University in Melbourne, Australia, and has now come to the US, where she is the new electron microprobe laboratory manager at the University of Minnesota and is part of the Earth and Environmental Sciences Department. Her research has focused on using X-ray microanalysis, both WDS and EDS, to characterize meteorites, which we will learn more about today. She has a vast experience and knowledge in both techniques and is passionate about teaching her users and the scientific community about how to use them correctly to get the best results. And I am thrilled to learn from her today. And with that, I will turn it over to Jennifer.
Thank you very much. Thank you for having me. I'm really excited to share with you some things that I think are cool about EDS and WDS. And I'm very pleased to hear that you think I've got an experience that's worthwhile sharing. So I'm going to, where have we gone? There we go, that should be a PowerPoint. So as Tiff said, I'm Jen. I run the probe lab here. I've only been here for a couple of months. So before coming here, I was working in the southwest of England at the University of Plymouth. So a lot of the data I'm going to share with you today is from the University of Plymouth. Back in that lab, we had 7 or so electron microscopes running the full gamut from EBSD through to EDS through to WDS. So although I run a probe now and I'm sort of purely a WDS person, I do still really, really love EDS. I think it's a great technique and it is a hill that I will die on. So what I'm going to do is kick things off, if this will progress, basically just by running through a little bit about EDS, a little bit about WDS, and what they're useful for and some tips and tricks that I've learned along the way. So both of these techniques rely on electron microscopy, so we can get high accuracy elemental compositions, but also with a really low spatial resolution. So it's really, really useful for sort of working out what individual crystals are made from, just getting huge data sets, really, really powerful tool. Importantly, it's non-destructive for the most part, unless you've got something incredibly fragile. You can analyze the same sample over and over again for hours and hours and hours. I've successfully done sort of, I think my record now is an 89-hour element map, and it was completely fine. There was no observable damage other than just a little bit of scorching on the resin. It's really versatile, and there's so much you can do with it, and you can do it as just single point IDs, but also across areas, which makes it really, really useful, especially because you can define where those areas are. Both of these techniques are utilizing X-rays released by the sample during analysis, and the way that works is we have our nice little electron shells in our atoms. These are all in the sample surface. Our electron beam shoots in, and an electron from that physically ejects an electron from an inner shell of one of these atoms. These electrons go on to create your secondary electrons. So when you're imaging your secondary electron detectors, this is what's coming through. That leaves a little vacancy on those inner shells. And then we have an electron from an outer shell drops down to fill that in. And that process is releasing energy. That's an X-ray. It's the X-rays that we're measuring. We're not measuring the electrons. We're measuring these X-rays that are coming from the sample during analysis. The reason that's really cool is that every element is unique. We can use these X-rays to work out what different elements are. Wizardry happens in the computer to then work out what your compositions are in terms of percentages of individual elements, which is really useful. But this all relies on crystal excitation energy. So it's the minimum energy required to overcome electron binding. We then have to worry about our overvoltage. So it's the ratio between the accelerating voltage of your beam and the critical excitation of a particular X-ray line in a particular element. And you'll see these on periodic tables. So pretty much every SEM lab has the same periodic table. And we all have these little K alphas and L alphas, sometimes M alpha, on the bottom of our elements. And these are the values that we use to try and work out what voltage do we need to be operating at. So in modern detectors, the optimum overvoltage is around twice the CE for infinite elements. So if you're analyzing the K alpha line in iron, that will give you an approximate overvoltage of about 13 kilovolts. We would then round up to 15. But you can run at lower energies if you want to by looking at these higher order lines. So EDS is utilizing the energy of these characteristic X-rays to determine elemental compositions. And what's really cool is that it measures all the X-rays all at once. So you're measuring every element that is in the area of interest, but also every single element line. So your K alphas, your K betas, your L lines. And it's really, really quick and easy. You can get someone set up to do good EDS analysis in about 10 minutes, probably. It's very straightforward and really easy to understand and quite a nice, easy one to see actually happening because it's so quick. It's great for large area or routine analysis. If you need to cover a big sample, EDS is the way to go for that. Or if there's just something that you want to do repeatedly over and over again, it's really easy to set up user recipes that you can just rinse and repeat and just collect huge swathes of data. As a common technique, pretty much every electron microscope facility is going to have some genre of EDS. So it's really, really available. And you can run it without standards, which is completely fine. That'll be semi-quantitative or qualitative. But you can also run it fully standardized. And this is my favorite part of EDS, is running it as a quantitative system. It can work really, really well. So these detectors are basically a series of individual parts that come together to make maths happen in the computer. So at the front, we have our little collimator. This is physically stopping some of the X-rays getting into the detector. If we didn't have that, we'd be measuring X-rays coming from everywhere within the sample, also everywhere from within the microscope. So you'd end up measuring X-rays coming from like the brass that lines the inside of the instruments. Behind that, we have a little electron trap. And this is basically deflecting electrons away from the detector, but still lets X-rays in. So if our electrons got into there, they would cause damage. They'd also mess up all the signals, and you'd really struggle to get any meaningful data. Then there's a little window. This is X-ray transparent, so again, our electrons can get through, but this is what maintains the vacuum inside your instrument. If we didn't have this, this would end up being open to atmosphere, and you wouldn't really be able to do anything. The most important part, probably, is this SDD. It's our silicon drift detector. This is a little silicon semiconductor, and that's converting the X-rays back into electronic charge. And that gets amplified by the transistor behind it, and that's sent off to the computer, and then wizardry happens and numbers come out. So what we're effectively doing is taking electrons, turning them into X-rays to turn them back into electrons again. But you can do EDS at low voltage, and because we are partnered with OI for this workshop, I do want to highlight the Ultimate Extreme detector that I was lucky enough to be able to work on a little bit before I left Plymouth. It is a windowless EDS, and it gets very, very close to your sample, so it's terrifying to use, but it's really, really powerful. So this operates at low voltages, much lower voltages than you'd be able to work with traditional EDS. And the benefit of this is by lowering your accelerating voltage, you can reduce your interaction volumes, which means you can increase your spatial resolution. You can resolve much, much smaller features. You're going to reduce your sample damage. So if you're working on things that are very fragile, low voltage EDS can be really, really useful for you. You're also going to get less migration of alkali and light elements. So if you're working on hydrated minerals or anything biological, this is really useful again. And it's surprisingly applicable to a whole range of science. So this colourful map in the background is a layered element map I collected of an impact melt on a meteorite at about 7 kV. These features in here are super, super tiny. This whole thing is only 200 microns across. I have extra maps where I can literally fully get into these little crystallites in these melts and like reveal the contents of this glass very, very nicely, which at sort of higher accelerating voltages, they all kind of get smushed together and it's really hard to resolve individual crystals. My colleague is a biologist back in Plymouth, and he was able to create this as a calcium, oxygen, nitrogen map of the cell structure in barley leaf. Importantly, he can do this without heavy element staining. So traditionally in biological work, you would stain your TEM slice with osmium or something else, basically to be able to see things properly and see where things are. But this was able to go into the instrument uncoated, unstained, just put it in, and it was completely fine. So it opens up a whole new range of applications. So although EDS is traditionally done at 15 to 20 kilovolts to get that enough of an overvoltage to measure pretty much every element on the periodic table, it's not always beneficial. If you have a sample where you don't have those really heavy elements, reduce the voltage, see if it makes a difference to the resolution of your imaging, makes a difference to the resolution of your data. And especially if you do have those small features, it might be worthwhile combining techniques and doing a high voltage run, but then also doing a low voltage run and seeing what the differences are. Anyone who's done EDS has probably come across element overlaps. This is just something that's inherent with EDS due to the resolution of the peaks. And although each X-ray and each element has distinct energies, some of them end up being really close together and it can be quite hard for the software to tell them apart. So the one that haunts me is aluminium, and the K alpha is right on top of the bromine L alpha. All my rocks that I work on are quite aluminium rich, and every now and again it gets really frustrating having the software tell you it's full of bromine. And you'll also find common ones like silica and tungsten is another common one, and phosphorus and zircon are also really good common overlaps. You can sort that out yourself. If you know your samples quite well, you can tell the software exactly, okay, well, it's not going to be this element, it's going to be this one, and then you recalculate. But this gets a little bit trickier if you don't know your sample, you don't know what's in there, and if you've got lots of heavy phases, it'd be quite difficult to tell them apart in the backscatter. Another one that's really common in EDS are sun peaks. This is where you get two X-rays arriving really close together, and the software just adds them up into one big peak. Some common ones that you might come across in earth sciences are magnesium, calcium, ends up with a little vanadium peak. That's one that happens a lot in my research. And again, if you know your samples, you can unscramble this yourself. The software does a really excellent job of sorting out most of it, but doesn't always get it right. But if you're struggling with these sorts of issues and these sorts of errors, this is where WDS comes in handy. And this is where we take the wavelength of the X-rays rather than just the energy of the X-rays. So WDS measures one element per time per spectrometer, so it's a much slower technique, but it does give you really, really good peak resolution. So this is from a standards plot that I was analysing back in Plymouth, where we had the sodium peak, but also the software was telling me there's a lot of samarium in here. Wasn't a particularly good standard. There was a good chance at that point that actually could have been some samarium in there. And so what I did is I took it through the WDS system, was able to resolve that actually what we were measuring was the sodium K alpha 1 and 2. But then in the background, that's where the samarium M alpha was coming through, and I was able to re-standardize, sort myself out, and work out it's actually just a sodium peak that's a little bit broader than usual. WDS is fully quantitative. You get higher accuracy than EDS. And you can find this typically in electron microprobes, so EPMA is electron probe microanalysis. But you can also get SEM-WDS, and this is where you have a single detector running on a regular SEM. So WDS is a little bit more complicated than EDS to worry about. So rather than measuring the energy, we're measuring the wavelength of X-rays, and that means that we have to satisfy Bragg's law, basically to measure the X-rays that we want. So we're diffracting the X-rays coming from the sample through a diffraction crystal into our little detector down at the bottom here. Inside this detector, it is fully mechanized. These are probably one of the few parts of electron microscopy these days that is basically just glorified strings and pulleys and cogs. And as I've learned recently, every now and again, those strings will break, and then you have to call somebody out because your instrument's making some very weird noises, and they basically just rethread it for you. So what's happening is our crystal moves sort of diagonally up and down through here, and our detector swings around on its round circle, and that accommodates an entire spectral range. We have multiple crystals that all diffract at different wavelengths, which means we can cover everything. But again, you are restricted by which crystals you have, which detectors you have, and how many detectors you have. So the WDS detector itself is different to the EDS detector. It's basically a little tube filled with gas, typically argon or P10 gas, and that has a central anode. So the X-ray has come off the sample, it's been diffracted by our crystal, comes into the detector, goes through a little electron X-ray transparent window, and that's ionizing the gas. That gas then ejects an electron that ionizes other gas atoms, called the gain. Some WDS systems require you to keep an eye on that and to change it as you go. And those little photoelectrons then get attracted to that central wire. That causes a drop in positive potential. That collected charge gets converted to an output, and that's then what the computer uses to work out how many X-rays you're getting, how many counts you have, and what that means in terms of your weight percent. So in this case, we're taking electrons to make X-rays, to make electrons, to make more electrons, and then we're sending those electrons off to the computer. So it's a bit more complicated. Thankfully, you don't really have to worry about any of this when you're running these instruments as a user. You just have to accept that it works, and that some very clever people have already worked out how these things work. So I mentioned SEM-WDS. I first got my hands really into WDS and first got my teeth into it by using a SEM-WDS detector. So I use the Oxford Instruments wave detector, I really love it. I miss it. If I could put one on my probe and have 5, I would. What's really cool about this is it adds EPMA capabilities onto a regular instrument. Importantly, it's inclined, so rather than the detector being fully upright, it's set at an angle, and this means that it's less sensitive to variations in height from your samples. So again, it's much easier to use, and there's a little bit less to worry about than sort of hardcore traditional EPMA that I'm currently learning. You can run this concurrently with EDS, which again is really, really useful. All happens in the same software. You can bounce between the different settings really easily. But it's incredibly easy to customize these guys. You can add in your own standards. You can add in your own images to it. Super easy to do. Doesn't take very long. And it really simplifies WDS analysis. The benefit of using the wave system is that it will not let you do it incorrectly. Whereas on the probe and on the EPMA, you can set it up completely wrong and it will do its best, but you're not going to get good values out of it. So I would always recommend to anyone if you're ever running your own lab and you have some spare money, get one of these. I think they're really useful. They add a whole extra layer of capability to your facility. They're really, really powerful. So EDS, WDS, both great techniques. They both have their drawbacks. So EDS, really, really easy to learn, phenomenally easy to learn, and it's really easy to learn how to do it well. There's only a few things that you have to worry about. Basically, all you have to keep an eye on is what voltage you're using, your probe current, and your dead time. And that's really, really easy to keep track of. Rapid data collection, super fast. You can set up things to run overnight and come out with sort of 500 data points without an issue. It can be fully standardized. And when it is fully standardized and it's calibrated appropriately, your major elements are completely comparable to WDS data. A lot of times people think that WDS is the be-all and end-all of composition analysis for electron microscopy. It's not. If you can do your major elements really well with EDS, save yourself some time, save yourself some money, and just do WDS on your trace elements. So this is some data from tridymite that I collected from a meteorite that I'm working on. Tridymite is a high-temperature polymorph of quartz. And what we can see here is we've got our SEM-WDS detector and some quantified EDS. And in this case, both the major and also the minor elements are all completely within error of each other. This is completely fine. You could put that in a paper, no one would complain, and you're going to get some really good data, and it can be done as long as you set up your data correctly. The downside of EDS is that typically your minor elements are going to be less accurate than WDS, and that sample preparation is really, really important. Having good sample geometry, having that really good flat surface is key, or at least being aware that if you do have something with topography, you're not going to be able to measure the entire sample. There are errors that are common in EDS, and that's going to be element overlap, so it does require a little bit of sort of human intervention sometimes to sort of unscramble those. But the main thing is it's actually really hard to convince people that it's good. I have a paper that's been in review now for coming on to 2 years, and we spent the first year and a half just convincing 2 of the reviewers that EDS was a valid technique and it was worthwhile having. And we've since made some progress, and now we've got different problems to fix, but that's fine. Just because it might be useful to some people, these 2 papers by Newbury and Ritchie both really dove in really well into how EDS can be a good technique, particularly in modern detectors. And importantly, both of these people work for NIST. So these are the people making standards used for WDS analysis. And if they're saying that EDS can be quantitative and it can be good, they're probably right. WDS, of course, will give you higher accuracy for major, minor, and trace element data, and you are only measuring what you want. EDS measures everything all the time. If you're only interested in one particular element line, WDS will unscramble that for you. It's fully standardized, fully quantitative, nobody ever complains about that. And it's a really good one to use in conjunction with other techniques. So if you want to do high accuracy data in situ, so do your WDS first and then take it over to laser ablation or mass spec, it's a really common way to do that. Downside, there's a really steep learning curve for WDS. There's much more you have to worry about, and it's really, really slow. You can only measure one element at a time, and even on a probe, when you've got 4 detectors running concurrently, that's only 4 elements at a time. So a single analysis point could take 3 minutes. It could take half an hour, depending on what you're trying to measure. It's also not as readily available or affordable as EDS. I found the tender documents, the probe that I run from back in 2020, and that was horrifying. So I dread to think what the new ones cost. And it's incredibly easy to get bad data on WDS. If it's set up correctly, it's great. But if there's anything that's gone slightly awry, you're going to see it in your data immediately. And sometimes it's quite hard to work out what actually went wrong. So if you combine both of these, you can get some really good high accuracy, high resolution data. It's non-destructive, you can combine them both really well. And I would generally use calibrated EDS for large area element mapping, major element analysis, and then use that to find the areas that you want to then target with WDS. Combining them both will save you time in the long run. If you can do all the quick stuff first and just work out what is worth taking the time to do the WDS on, it's going to be much more beneficial for you. You'll get more data out of it, and you'll get a more sort of cohesive study at the end of it. So that's kind of the end of EDS and WDS. They're great techniques, please use them. But I'm going to actually talk to you about some of the science that I do now. So this talk is how to build a planet using EDS and SEM-WDS to classify new meteorites. This is all part of research that I do with my research group. We're called Space Rocks, because we're not overly imaginative, but it's quite good fun. So Space Rocks began in Australia with Professor Andy Tompkins and colleagues over there, since broadened out into the UK team that I was part of until 4 months ago, and now there's myself and Aidan in the US. Both of us are still British, but we are sort of doing meteorite things over here. So the reason we care about meteorites is because they're really cool. So planetary geology and meteoritics is the study of the geology of planets, moons, asteroids, comets, meteorites, and that can be everything from ground-based analysis, from using telescopes, to probe-based or rover-based analysis, but also the physical analysis of meteorites as well, that come through the atmosphere, land on Earth, and somebody finds and eventually gets them classified. The reason we study meteorites is that these record what happened in the early solar system. They record everything from the very first solids through to planetary formation, through to the destruction of planets. We call that catastrophic disruption. A whole gamut of igneous metamorphic processes, aqueous alteration. They record so many things that we otherwise would not be able to see. There are things happening on small bodies that don't exist anymore that we can observe and sort of rebuild by using meteorites. So if you're out and about and you want to find a meteorite, what you want to do is find an old, dry space, ideally. Want to be old, so they've had lots of time for meteorites to land on them. Want to be dry, so they haven't got washed away or eroded. And ideally, so there's no plants growing on top of them, because it can make it really hard to see. So often, Australia, Antarctica, and Northwest Africa are like the 3 big meteorite fields at the moment. Antarctica is great because all these meteorites land in the glaciers and they just sort of get spat out at the edge of mountains. Northwest Africa, again, all the deserts have had loads of time to collect meteorites, and it's really easy to see them. And Australia is, again, big central sort of old surface. It's just collecting rocks. All these are also great because the local sort of terrain colour is very different to the colour of meteorites. They're typically quite dark in comparison to what they land on. They're unusually heavy as well. They're very, very dense, heavier than you would expect a rock of that size. They might have things like a fusion crust, which you can see on the outside of this one here, that little black layer of glass. And they're often magnetic. So if you do see anything that you think is a meteorite, put a magnet on it, see what happens. If you think it's definitely a meteorite, don't put a magnet on it, just put it in a little plastic bag and find somebody who's happy to analyze it for you. So the reason we classify meteorites is pretty much the same reason that we classify regular rocks. We like having categories of things, but you cannot use a meteorite in scientific literature unless it's been formally classified and it's been given an official name. Meteorite names, admittedly, are quite boring. They get given a sort of code at the front based on where they're from. So they get a little geographic indicator, and then they get a number, which is just which number from this area is it. We classify them based on mineral chemistry, but also mineral texture. They might have some meteorite-specific features like chondrules, but we can also do oxygen isotopes. So every part of the solar system will have a distinct oxygen isotope reservoir. We can use that to work out where they come from. So we can tell the difference between meteorites from Mars, meteorites from the Moon, meteorites from Vesta, different types of chondrites, all through oxygen isotopes. These are all the different types of meteorites that we have. We have 45 or so different categories of meteorites, and all of these will have subcategories as well. There's a lot happening. So if we start off with chondrites, these are composed of chondrules. These are these little spheres of olivine and pyroxene. These stick together to make rocks. So we have enstatite chondrites. These are in a solar system really, really reduced meteorites. There's no olivine in these, it's just pyroxenes. We have ordinary chondrites, and they're called ordinary because these are the most abundant type of meteorite that you'll find. The vast majority of the meteorite collection is made up out of these guys. And again, these are all sort of in a solar system, and there's a lot of variation happening between these. Interestingly, we also have carbonaceous chondrites. These are outer solar system meteorites, so these are from beyond the snow line. So they have clays, they have hydrated minerals, they have amino acids. But they also have these sort of white fluffy inclusions. These are calcium aluminium rich inclusions. And these are the first solids that formed in the solar system. There's a whole range of minerals that they could be, but they're all high in calcium, high in aluminium. And the oldest ones have been dated to 4.568 billion years. And that's the date that we say that the solar system was born as we know it. If you stick enough chondrules together, you make a chondrite. If you stick enough chondrites together, they melt, and this is when you get into your primitive achondrites. So achondrite just means a rock that doesn't have chondrules. Primitive achondrites are the first things that are melting. They're quite a weird group, and there's some strange things that happen in these guys. But my personal favorites are the uralites. These are carbon-rich achondrites. So all that carbon also turns into nanodiamonds. So they're an absolute nightmare to try and prepare for analysis because you're trying to polish diamonds with other diamonds. It doesn't always work very well. But these are a fascinating group of meteorites. We think they might be the mantle of a parent body that's been completely destroyed. But then it looks like some of them, so as they got broken off, came back together to form a second body, and then that got destroyed as well. So really interesting, really enigmatic, and quite good fun if you ever get your hands on one. If you keep melting things and let geology keep happening, you end up in your evolved achondrites. And these are things where we have like things from the moon, things from Mars, things from large asteroids, so the HEDs, the meteorites that I work on. And these are where basically starting to get differentiation happening. So you've got crust, mantles, and cores. And the cores of planets end up in these stony ions and ions. So iron meteorites are just how they sound. They are just chunks of metal from the inside of planets that have been completely destroyed. Stony ions are a little bit more mysterious, but they're very fun. They're absolutely beautiful. They're these big metal networks with these chunks of silicate minerals inside of them. So pallasites are really famous. They might well represent either the core mantle boundary, so as the metal core is rotating inside this planet, and it's basically grinding up and incorporating the overlying silicate mantle, or it could be the result of a hit-and-run collision where you've had two planets slam into each other and the core has mixed in with the mantle of another body, and then pallasite being created. Most sideroids are similar, but they seem to include also basaltic materials. They also get pyroxenes and feldspars in there. So there's lots going on. Meteorite researchers tend to choose their favorite. So I'm stuck on these howardites, eucarites, argonites. I think they're really interesting. And you can quite easily build a career just studying a single group of meteorites. We're always getting new material. There's always stuff happening. So despite all these classes that we have, we actually have very few parent bodies. So there's not very many bodies out there that are still sort of around to look at. We have the moon. When we know we've got stuff from the moon, we've got Mars. We've got meteorites from Vesta, which is the second largest asteroid in the solar system. And now, maybe with the help of some sample return missions, maybe asteroids like Bennu and Ryugu, they might be the parent bodies for some of the carbonaceous chondrites, or at least very similar to what those parent bodies would have been like. So a lot of my research and a lot of what I do in my spare time is classifying meteorites. And this is kind of the sort of data sets that we're producing. So large area element mapping is a really, really key part of meteorite classification. There's so much you can learn from it. So this is a meteorite that we found in South Australia. And you can see we've got lots of olivine in green, lots of pyroxene in blue, not very much feldspar, and then some accessory phases in there as well. So this meteorite's quite cool. It's a chondrite, and normally I'm not a big fan of chondrites. I don't think they're igneous enough for me. So this is what we would call a type H6 to 7. So H just means high metal, high iron, and you can see there's lots and lots of metal in there with all that white and grey. 6 to 7 is a metamorphic category, so it goes all the way from 3 up until 7, 3 being completely pristine, 7 being pretty much an achondrite. And this meteorite has samples of both. So this outer portion here is a type 6. We can see some chondrules, but not many, most of them melted. But then inside the central portion, we've got much more feldspar, we've got a slightly different composition happening. But we've also got igneous textures. So this meteorite is recording that transition from chondrite into achondrite. And that makes it really, really interesting. Other ones that we find really interesting are ones like this. This is an L6 chondrite. So again, quite metamorphosed, not very many chondrules left in there. It's on its way to becoming a basalt. L, in this case, just means it's low iron. And interestingly, this is composed of 2 different lithologies. So we have this chunk in the middle, which is, very obviously different texture, different colors, meaning different composition compared to everything else out there. But both this outside portion and this inside portion are the same category of meteorite. They're both L6 chondrites, they're just different. We also get some more unusual things. This is a CO3 carbonaceous chondrite, so from the outer solar system, and you can see the colors look very different, the texture looks really weird. And what's really fun about this is all these sort of turquoise pieces. These are all those calcium aluminium rich inclusions. These are all those first solids that were forming in the early solar system. And there's loads of them, they're everywhere. Carbonaceous chondrites have undergone aqueous alteration as well, so they're full of clays, they're full of organic rich material, full of carbon. So trying to prepare these is really, really difficult because you don't want to get them wetter than they already are, but they're also incredibly fragile. They polish away and crumble into dust like nobody's business. So if you ever do have to like prepare anything along these lines, it's always a good idea to reach out to one of the museums that does curate these and ask for their advice. But it can be done, and you can get some beautiful data sets from them. This one is one of those stony iron meteorites. This is a mesosiderite. So all these big green chunks in here, this is iron metal. This is from the core of a planet, or a planetesimal that was forming and then got sort of blown apart. The silicate in here is basically a basalt. It's pyroxene, it's feldspar. And this is really interesting. So this is the crust of a different body mixing in with the metal from another planetesimal. So these are most likely hit and run collisions, where you've got two bodies that are sort of like grazing against each other and sort of scooping parts up. But this is a really, really nice example. And what's come out recently in literature is that this basaltic material that you find in mesosiderite is not anything like the basalts that we find on large asteroids. Though they might have the same basic minerals, they actually have very different trace elements. And they have different isotopes in some cases. So they're forming in a similar area, but not from the same body as you might find with other things. And then lastly, this is one that I've been working on recently. This is a eukarite melt breccia. So eukarite's one of my favorite groups of meteorites. These are plagiobasalts. I think they're really pretty. But this one's really cool because it's full of impact melt. So we have these nice big clasts in there for pyroxene and plagioclase. Then this high temperature, high pressure process of impacting, which also quenches really rapidly. So you end up with these tiny, tiny little bits of sort of microlights almost, forming a black impact glass, which polishes really sharp. So as a word of warning, anyone polishing impact glass, wear gloves. I have lacerated my hands trying to clean these up. But we can also see just the partial melting inside these impact melt veins. So people might use these to work out sort of shock and pressure conditions, how sort of, shock and pressure might affect basalts, and what was happening on an asteroid really, really long ago. So in terms of my actual science that I do, I've been working on this one meteorite now for about 3 years. This is Northwest Africa 6414. It's a polymit eukarite, so it's a breccia composed of lots of different types of basalts. And this is the backscatter image. It's only sort of like 1.5 inches across. And you can see even just in the backscatter, there's just lots happening here. It gets further complicated when you look at the large area EDS map. There's so many minerals going on in here. It's really, really confusing. Where do you start with something like this? Especially because when you go into the imaging and actually work out how many different types of rock there are, there's so much. So we have everything from subaphytic basalts to sort of more cumulate textured things through some weird shock affected stuff. We've got breccias inside of breccia. We've got cumulate textured things. I don't even know what half of these are. And there's so much happening. We've got melts, we've got some plectites, we've got some weirder stuff. It's a lot to get through. So to try and unravel the history of this meteorite, started off with large area imaging and large area mapping. Large area EDS mapping is great. We'll be able to calculate in modal abundance, so through pixel counting techniques. It'll also give you a bulk composition without sort of across the entire sample. So you'll get a larger spot size sometimes than you might do with XRF. But it also lets you find those areas of interest, which you can then go back into with high resolution EDS imaging and point ID. But also find those areas that you want to do WDS, be it SEM-WDS or EPMA, as well as EBSD. So setting up your experiment in this sort of structure can be really beneficial sometimes to basically make sure you're getting the data that you actually need. So by the end of this, I have about 600 EDS data points, as well as WDS, as well as element maps, as well as EBSD. There's so much to go through. I couldn't possibly begin to properly unravel the history of this rock. What we're going to do today is I'm just going to focus on the basic major elements of the pyroxenes. So this is what pyroxene trends should look like in typical HD meteorites, so the meteorites from the same asteroid. Diogenites are orthopyroxene cumulates. They can sit down here, they're quite magnesian. Then we get these sort of gabbros that come through the middle. Basaltic eucrites, and this is technically a basaltic eucrite, form this nice sort of line through here. There's a couple of different compositional trains inside there, but they're generally quite well constrained. This is what the data of this meteorite looks like. It is all over the shop. And believe it or not, you can actually start pulling different things out by having that combined mapping, that combined imaging, and then the point ID is you can take this data and you can start separating it out so it's not just a cloud of nonsense. So we can put out into things that actually do have igneous trends. So we have our subophytic class. They form a couple of different trends. This equigranular class has on a completely different trend through here. And these granulitic things as well are plotting separately. So we have at least 4 trends, and we have at least 4 magmatic sources recorded in this meteorite. We can then look at the ones that have been really shocked, and we can see how those nice igneous trends have been sort of disrupted and stretched across towards calcium and iron. And that gives us an idea of what's actually happening during the shock process, by which elements are being sort of mobilized. And so there's a lot that we can learn from that. It's just really hard sometimes to constrain the compositions of these and sort of reverse engineer them. But if you take an average composition of pyroxenes in these shock classes, they do plot back on that nice igneous trend. So we can sort of reverse engineer these and work out what that material might have been originally. We can look at the impact melts that we find. There's lots of different types of impact melts, and these plot all over the place, which isn't overly surprising because these are going to be, it's not just pyroxene, these are going to be formed from sort of an amalgamation of all different types of minerals, all different types of lithologies, and then recrystallizing out into separate phases. But again, they do kind of fit mostly in line with that main basaltic trend. But again, there's going to be a couple of outliers. This is where that low energy EDS comes in really handy. These features are tiny, and because we don't know how deep they go either, having a small interaction volume for this sort of analysis is really, really useful. There's some weirder things in this meteorite. We have some olivine-bearing lithologies in this meteorite as well. So we have this weird class at the top, which has a big chunk of olivine in it. Very distinct pyroxene compositions. We have these vein fragments, which I've labeled the wrong color. So the vein fragments are these little blue triangles down here, little blue diamonds through here. And we see some compositional zoning happening in those guys. These purple ones are 3-phase symplectites. These are olivine, pyroxene, and silica symplectites. And these plot absolutely everywhere. They don't fit on any trends. And there's a lot of things where you might think, actually, these pyroxene compositions shouldn't be allowed to be happening. How these form, we don't really know. There are some ideas, but I don't have enough time to get into all the current drama surrounding symplectites in small bodies. We've also got a class of breccias inside this breccia. And then if we look at those compositions, they're also HED class, which is quite nice. So no evidence of a meteorite impactor preserved in this meteorite so far. But we do have sort of like this nice mixing of different compositions inside our meteorite. And then if we compare everything else that we're seeing, we've got fragments in the matrix basically composed of every other sort of lithology that we're looking at. So there's no real diatomite material in here, but we do have basically the entire run of eucrite compositions. So just by taking all those pyroxene compositions and unscrambling those, we can work out we've got lots of igneous activity. We've got multiple magma sources, we've got different compositional trends, different textural trends. You can run it through 2-pyroxene thermometry and you get a whole range of numbers as well. But we also get distinct pyroxenes associated with magmatic phayolite. So we've got evidence of other magmas that aren't preserved elsewhere in the meteorite collection in this one rock. And this is all what we're working out basically just from EDS compositions. We can look into metamorphic activity. We have exsolution in a lot of these pyroxenes where we have basically the rock has been cooked and held at temperature for a while, and calcium reorganizes itself inside the crystal structure, and you end up with bands of calcium-rich pyroxene and bands of low calcium pyroxene. This varies between the different class, between different minerals. Some have really thick bands, some have really thin bands. So we can infer that different parts of this rock underwent different metamorphic histories before being made back into the current rock that we see. There's lots of variations in shock zoning. Not everything is shocked to the same extent. And some class and some fragments don't seem to experience any metamorphism at all. They seem to be the original igneous textures. And that's a really uncommon feature on Vesta. This asteroid sort of cooked itself for a good few years to about sort of like 800 to 1,000 degrees. Most of it has been metamorphosed with very few exceptions. So that's quite exciting. We've got evidence of impact gardening. So we have class of pre-existing breccias being worked into this breccia. We have evidence of aqueous alteration. So we have phayolite veining in some of these parts, where we have fluids likely derived from impacts from carbonaceous chondrites, those outer solar system meteorites driving aqueous alteration. And we have ejecta blanket processes. We have different symplectites. We have 2-phase ones, which are thought to be formed through basically the injection of sulfur-rich fluids through ejecta blankets. We have 3-phase symplectites, which might be from the rapid decomposition of pyroxenes. So just through EDS, you can build up an entire geological history spanning several million years that happened 4 billion years ago, just from quick EDS that we were able to run overnight and through one day. All this to show that large asteroids are much more like planets than you might think. They're not just lumpy bits of potato-shaped rock. They are their own little geological systems. So really good to collect EDS data, but it's also really easy to collect bad data. If you have bad sample prep, you are going to have bad data. Sample preparation for EDS and WDS is really, really important. Making sure you've got appropriate operating conditions, so a sufficient overvoltage to measure the elements that you want, you've got enough counts to measure, keeping an eye on dead time, and really rigorous focusing, making sure your Z height is correct, making sure your working distance is correct, and making sure they're correct for the particular instrument that you're using, because it will vary between detector setups. Make sure you calibrate your EDS. You want to recalibrate it if you change the voltage. It's an easy thing to forget to do, but it's really important that you do that. And also check your data on a standard. If you are calibrating on a standard, you've probably got a standard block in there. Set it up, then sort of as you would with an electron microprobe, just give it a check. Have a quick check. Make sure it's doing what it should do on something that you know the composition of. And make sure you monitor your beam current. Understanding how stable your instrument is can be really, really powerful. And it's going to save you a lot of trouble in the long run. Make sure you regularly re-standardize your system. If you are running standardized EDS, you don't have to standardize every time you do your analysis. The software will store those, but make sure you do them every now and again. So I try and get them done sort of every 6 months or so, once a year at the very least. And that means that it can accommodate basically for any instrument drift that's occurring. Keep an eye on the limitations. So EDS might be brilliant for major elements. WDS is great for minor elements. But then also be realistic about how much time you have and how much data you need. Do you realistically need 600 data points for a meteorite? No, I went slightly off the rails and got really, really excited. And then I've basically been dealing with it. I've got massive spreadsheets and it's really hard to know where to start. And also collaborate with your technical staff. As technical staff, we're here to help you. We want you to get the best data that we can. If you have questions, come talk to us. If you are struggling with something, come and talk to us. We are here to help you. It's our job to make sure you do well. Presenting data in EDS data in literature is something that's a little bit contentious. So I wanted to give just a couple of tips about what I found has been successful. And the main thing is just to be really honest about what you're doing. So state your calibration techniques. How many counts did you count to? What's your beam variance? What material did you standardize on? What material did you calibrate on? What are the dead time allowances for your particular setup? And full list of operating conditions. Be honest about the corrections, normalizations that are applied to it, and be ready to defend it in review. EDS these days is great. EDS in modern detectors is not how it was 20 years ago. It's not even the same as it was sort of 10 years ago. But if you can do it well, you may get glowing reviews such as this from my reviewer too, who was ardently anti-EDS when I began this project and began this paper. And we were able to convince him by showing him just how good it can be that for routine classifications, such as meteorite classifications, EDS is completely fine. So to round it all off, because I've rambled on for far too long about rocks that I think are cool, EDS and WDS are really good complementary techniques. If you can, use them together. If you've only got one, that's completely fine as well. But just make sure you organize experiments in a way to make the most out of your time available. Large area analysis, really good and a really key part of EDS. It's going to be really useful to help design the rest of your experiments. If you're just doing individual points, it can be quite easy to miss something, or there'll be a feature that you just don't look at. Finding those areas of interest that you can then target with other techniques or to retarget can be really beneficial. Do your non-destructive analysis first, please. I have lots of users come to me and they want to measure things, but they've done laser ablation and the mineral they want to measure is no longer there because it's got this huge crater in it. So make sure you do this first and then take that data and apply it to your EBSD, apply it to your laser ablation and use it in conjunction with the other techniques. Work with your technical staff. And finally, if you think you have found a meteorite, please email me. I am more than happy to take a look, send me a photo. If it looks convincing, send it in, I will cut it open, we'll have a gander, and if it is a meteorite, I'll get it classified for you. So that's all from me. So I'm more than happy to answer any questions. Thank you very much for listening. I hope that was useful and maybe a little bit informative.
Hi, Jennifer. Thank you very much for your talk. Really appreciate it. I'm going to be helping out and moderating some of the questions that you've been getting today. Just a quick introduction. My name is Kelly. I'm a second-year PhD student in material science and engineering in Professor Vinayak Javid's group. Just as a reminder, everyone, please submit any questions that you have in the Q&A box below. I'll get us started. So the first question that was asked is, In WDS, why is the analyzing crystal needed? To make the X-ray beam, is it to make the X-ray beam coherent?
Okay, so the analyzing crystals in WDS are diffracting the X-rays of the wavelength that you want onto the detector. So we're not measuring everything. So through Bragg's law and the different crystal lattices available with those crystals, is we can separate out the individual X-ray wavelengths that we're interested in, which means you're only going to measure what you actually want to measure. You're not going to get a flood of other data. So basically, you can think of it as almost sort of tidying up and separating out the X-rays of interest from everything else, which I think is probably quite a basic way to explain it, but that's how I think of it in my head as the easiest way to do it.
Gotcha. Okay. Thank you for your answer. Another question is, would you have any suggestion on how we can evaluate good versus bad sample preparation?
Yeah. So for both EDS and WDS, ideally we want to be polishing things down to 1 micron. You can get away with it on some things. Ion polishing is another way if you need really, really good data. But probably the best thing to do is actually just, if you have the time, take something that you've polished down sort of to 9 microns and have a quick look at it in an SEM and see what it looks like. See, where are you actually getting those flat surfaces? How much of your sample is scratched? Then compare it to something that you've taken down to that 1 micron and can run the same analysis, see what you're getting differently. You can also do it in SEMs if you just like tilt the stage slightly and see how that changes the X-ray signals that you're getting. Some, depending on where your detector is, it might improve some elements, it might make some worse. As a general, as long as you're analyzing bits that look flat and boring, you'll probably get good data out of it. If you're trying to analyze anything that has obvious texture, you're probably going to struggle. There are ways to work around that. You can use beam defocuses, you can sort of do area analysis instead and get an average composition. It just won't be sort of individual point analyses. So there are ways to work around it. And again, your technical staff will be able to help you with that. And if you do have any questions about sample prep, your technical team will know sort of like their favorite ways to get things prepared. Generally just trying to aim for like a 1 micron polish. It doesn't need to be vibrationally polished. You can do it mechanically, you can do it by hand. I don't have any automatic polishers in here, so I'm polishing all my samples by hand and they are rough. But as long as there is enough of a flat surface, you will be able to get some good data from it somewhere, I promise.
Got it. Thank you. Someone had no questions, but wanted to thank you for a fabulous talk. And then the next question is someone wondering how to control dead time.
Yeah, so there's lots of different things you can do to control dead time. You can change the accelerating voltage to either increase or reduce the number of counts that you're getting. You can change the probe current. And again, if you need to decrease your dead time, you can decrease your probe current. If you're not getting very many counts and your dead time is very low, increase your probe current and that will lift that up. You can also sometimes change how what's called the process time. And that's basically just how long the computer is taking to sort of count each batch of X-rays. The Aztec software is really good for letting you have control over that. So you can set up your absolutely perfect operating conditions that you want to work at, and then you can change the process time to mitigate the dead time. At the absolute sort of like end of things, you've tried everything else, nothing is working, your detector is just completely saturated. You can try retracting your EDS detector as well, and by moving it away from your sample, sometimes that can make a difference. Particularly if you're running EDS and WDS concurrently, the conditions you use for WDS might be much higher than what is suitable for your EDS detector, and sometimes just retracting it slightly can sort of bring the EDS dead time down while still maintaining good WDS data collection.
Thank you. The next question is it possible to measure light elements quantitatively, such as fluorine and chlorine, in EDS or WDS?
Yes, but it is hard and my least favorite thing to do. So fluorine and chlorine are both really, really mobile under the electron beam. This is where that low voltage EDS is going to come in really handy, and you can standardize your EDS systems on those light elements so they can get all the way down to beryllium comfortably. Lithium, sometimes. I've not been able to measure lithium in a rock because it's sort of shadowed by everything else, but if you have sort of like battery material, you can measure lithium on things like the oxidant spin extreme detector. It is possible. You just have to adjust your operating conditions. And it might be a case of you might need separate operating conditions to analyze fluorine and chlorine quantitatively than you need to measure the rest of your sample. They're often in minerals or material that's often quite fragile as well. So it might be a case of actually spending the time playing around with it a little bit and trying to work out what your operating conditions are where you're not causing huge amounts of beam damage, but you are also actually getting that signal out. And it might be a case of changing how you're coating your sample, doing thinner coats if you need to, or changing the coating material might help sometimes. Worst comes to worst, find somebody with a soft X-ray detector and run it at really, really low voltages. I have one here that I've not tried yet because it scares me, but I've got to try it on Monday to do just that. I'm trying to measure fluorine that is in too low proportions to be measured with the electron beam in any other way. So I hope that helps. Basically, reduce your accelerating voltage and be patient and just try some trial and error, and eventually you should be able to get something.
Great, thank you. Next question is, what is the best way to do sample prep for a powdered sample for EDS?
Okay, so there are different ways you can do it. When I've done EDS on powders in my previous role, depending on the type of powder, if it was a really, really fine one, I would take just a pin stub and sort of either some carbon tape or double-sided copper tape, and basically just gently press that powder onto it, then coat it, analyze that. If you do a sort of very thin layer, there should be enough of a surface available if you kind of average it out. So for powders and things are sort of three-dimensional, I would always recommend just doing like a very quick, low-resolution EDS map across it to work out which bits are being shadowed from your detector. Once you have that, you can then find the areas that the detector can see and therefore get data from to do point analyses if you want to. If your powder is more along the lines of sort of like a sandy texture and it's coarser grained, you can do them as grain mounts. So you can mix them up into slurries in resin and then polish them flat so you actually do have that perfectly flat surface again. It very much depends on what the powder is. If it is really fine, carbon tape and just tap off the excess. Otherwise it will get sucked up into the chamber and that's not fun. Or if it's a coarser grain powder, you can mount it in resin, or sometimes honestly a bit of super glue on a glass slide and just sort of press it in gently. That can be more than enough to make sure it doesn't sort of move around in your instrument, but to give you enough of a surface as well to actually get some data from. Full disclosure, I'm very much a resin block person. I try and avoid powders whenever I can.
Gotcha. Thank you. Another question is, if the surface is not flat, how can it affect EDS results? And in particular, how is the X-ray signal affected?
So if your sample has lots of topography, so it's really, really bumpy and goes up and down, what's going to happen is as your electron beam scans across it, the X-rays being released, not all of them are going to be able to get out of the sample. They're going to get trapped in the sample. They're going to get sort of shadowed from the detector. Because the detectors aren't moving, they're all in fixed positions. The topography of the sample gets in the way of things. Sometimes if you do have a sample that is tilted, you can rotate it and try and sort of find a sweet spot. For WDS, having a flat sample is much more important. EDS is a little bit kinder. For WDS, you need to have a flat sample because we really care about the takeoff angle. So at the angle at which the X-rays are leaving the sample, because that's what basically gets them into the diffracting crystal. And if that's not at the right angle, so your sample's not the right height, or your sample's got too much topography, you're just not going to get basically your signal into the detector. There are ways around it, but you'll probably see it most often with EDS mapping, and definitely some of mine where I've not done a good enough job polishing, there'll be bits that are shadowed. If you can just work around those areas. Yeah, every now and again you'll have a look at something. Unfortunately, you will have to take it back out, repolish it, try again, until you work out the best sort of preparation techniques for your particular samples.
Great, thank you. And we'll just do one last question. It's a follow-up on the fluorine and chlorine question. They're using carbon tape and it's coated with osmium, and the EDS is giving a huge carbon peak, which is hiding all the low peaks, such as the oxygen and fluorine. So they're wondering if it is possible to use something like a silicon wafer to prepare the powder.
Yeah, I can't see why not. Yeah, I can't see why that wouldn't work. It's not really my area of expertise, that sort of stuff. Yeah, I would imagine, yeah, that a silicon wafer, if you can adhere it to that quite well, or even if it's a very fine powder trying to use actually like the coating to hold it in, that could work. Yeah, I that's a bit outside my particular area of expertise, but I would imagine that a silicon wafer would work fine if you can use a glass slide instead. Just something that isn't going to give you that big carbon peak. Carbon tape is great, but it does also degas sometimes, so you might end up losing some of your sample. If you want to reanalyze it, you'll see it over time, it will bubble in the chamber. Yeah, so maybe if you can try and find a way to adhere it onto silicon wafer, that might be a little bit better in the long term as well. It might make your samples last a bit longer. So it's not very much of a good answer on that one. I'll have to think about it though.
Gotcha. Okay, well, thank you very much again for your presentation and for answering our questions. Yeah, thank you. And we're just going to take a short break and then move on to our next speaker.
So, welcome back from your break. This is the final talk for today. This afternoon, we'll be doing in-person demos. And this talk is going to be given by Richard McLaughlin from Oxford Instruments. So Richard has been working for Oxford Instruments as an application specialist for the last 25 years and just has so much knowledge on how to use these tools specifically, but also EDS, WDS, and EBSD in general. So it's my pleasure to welcome Richard. Richard, like myself, has a background in geology. So we've got a lot of geology talking today, which is really fun. But thank you, Richard, for joining us. And if you are able to share your screen, then you can go ahead and take it away.
Great. Can you hear me?
I can hear you.
Okay, great. So let me see if I can get this started here. Pop up and let me go with this, I think, and then see if I can get my screen up. Now, okay. So I'm going to be talking about unique detectors for high resolution EDS and real-time elemental imaging. I think people who are familiar with the EDS detectors or have an EDS system, they would recognize a standard EDS detector. It'd be a detector with a round sensor. It would have a collimator. It would have an electron trap. And a standard EDS detector is good for all types of applications. It might not be optimum for certain applications or for certain analytical conditions. And this is where these unique detectors come in, where Oxford Instruments has created detectors for high spatial resolution analysis. And we just have a new detector out now called BEX, which is kind of designed for real-time chemical imaging and fast X-ray mapping. So the agenda today, I'm going to just have a short introduction to energy dispersive spectrometry. It's been covered quite well in the previous talk, but I'll be talking a little bit more about the hardware. I'll start off with the ultimate extreme detector, kind of give you an overview of what's different to an extreme detector versus a standard detector. And then I'll just kind of go over some of the applications that you would use the extreme detector for, like low KB, low beam, applications, high spatial resolution applications, and I will touch on lithium detection. There's some caveats to that, but we certainly can see lithium in some compounds. After that, I'll get into talking about what we call a BEX detector, and I have the term unity in brackets. It might get a little bit confusing because I might switch back and forth between BEX detector and unity. BEX detector is going to be the actual detector itself. And unity is kind of the concept in which the BEX detector fits. That is, BEX detector is not used alone. It's used with a standard detector. And that's where the concept of unity comes in. And then some of the applications that we'll be covering would be live chemical imaging, fast mapping, and something I call kind of surveying applications. I think we kind of saw some examples in the previous application saw a lot of large area maps. And that's kind of what BEX in Unity is kind of designed for, to really collect these large maps quickly. So if you're not too familiar with energy dispersive spectrometry, we're talking about the EDS that goes onto a scanning electron microscope. This is just an image on the left of what we have in our lab in Concord, Massachusetts. It's a Sigma 500 variable pressure. And there's quite a few detectors on this system. On the left-hand side, we actually have an Ultimax 170, which I would consider a standard detector because it's windowed. It has a round sensor. But we also have what we call the Ultimate Extreme detector behind it. It's just on near the back of that SEM. And then below that, we have what we call a symmetry EBSD detector, which Mike Hjelmstad is going to be talking about tomorrow. And if you opened up the chamber and you took a look inside the chamber, you would see that the probe of the EDS detector would be inserted relatively close to the EDS, to the sample. And of course, the beam of the electron, the SEM would hit the sample, generate X-rays, and the X-rays would enter into that EDS detector. So we saw this slide. I might go into a little bit more detail about the hardware. As we've seen in the previous presentation, essentially what happens is the electron beam interacts with your sample, and that interaction generates X-rays, and those X-rays are going to have an energy distribution. There's going to be some characteristic energies of those X-rays, which are going to form our elemental peaks in our EDS spectrum, and then we can use that to do some qualitative analysis or some quantitative analysis of the sample. And if you move the electron beam across your sample and collect a spectrum at each point, you'll be able to actually map the intensity of those peaks or map the abundance of the elements. So we have an X-ray map down in the lower right hand side of that slide. Now on the left, we have a kind of a standard detector diagram. And really to understand what the difference is between these unique detectors, you kind of have to understand how a standard detector works. And it's already been gone through a bit, but the most important part, I guess, of the detector is going to be the snout or the probe end. So that would be at the bottom of that diagram there. There's a collimator and there's electron trap. So the electron trap is there to trap the electrons that come into the system. And it could trap electrons up to 30 keV energy. The collimator is there to make sure that the X-rays that are entering into the sensor are from the spot you're analyzing. And the sensor itself is behind a window, and that window is used to separate out the environment of the chamber from the vacuum that's behind that window. And in that vacuum, you have the sensor, which is used to convert X-ray events or X-ray energies into electron hole pairs. And then that's measured as a charge, converted into a voltage, and that's sent off to a digital pulse processor. And a standard EDS system has one digital pulse processor for one detector. So that's a typical EDS setup. Now, as I said before, standard EDS detectors are fine. They're very versatile. They can do almost all types of applications, but there are limits to standard detectors. And those limits can be kind of broken down to three, I guess, important things. Solid angle. So solid angle is just kind of a way of collecting as much signal, X-ray signal as possible. And that's going to be controlled by the size of the sensor. So the bigger the sensor, you're going to collect more X-rays. The position of the sensor. So if you move that sensor close to the sample, the solid angle increases and you can collect more X-rays. And that's going to essentially govern the number of counts you can collect per second per nanoamp. So solid angle is very important. Another important factor on how many X-rays you can actually collect is the sensor window. So standard detector has a window, sensors in a vacuum. That window is very thin, but it is a barrier to X-rays, essentially the lower energy X-rays, or the soft X-rays, I guess is one term that you can use. And in the lower right-hand corner, we've got a plot of the absorption or the transmissivity of X-rays through that window. And you can see that, you know, around 1000 keV, so 1 keV, there's a severe drop off to the proportion of X-rays that can actually penetrate that window. So you get down to beryllium, I think you're probably down to 6% actually getting through, somewhere around there. So yeah, those low energy X-rays, most of them are lost. And that's not even including the X-rays trying to get out of the sample. This is just the window. So the unique detectors are kind of designed to overcome these limitations. The last point, the last limitation is what I call the counting chain, which essentially is, you know, how many X-rays can you process in the sensor? How many can you get through to the digital pulse processor and get into your map or into your spectrum? So you can almost view that as kind of like a pipe, which is going to limit the flow of that signal. So just to expand on the counting chain, you've got the sensor. Of course, the X-rays come in, create electron hole pairs, and then those are converted into a voltage that has to be processed, and that gets into your spectrum. So there is kind of a maximum throughput that you can get when doing EDS analysis. And on a typical EDS system, you're probably getting around 500,000, maybe a little bit less than that, output into your spectrum or into your maps. Another downside is the more you push that signal through that pipe, the fidelity of the data degrades, and the peaks get wider. You get pulse pileup, some peaks and things like that. So there are limits to EDS analysis, and the unique detectors are trying to kind of overcome some of those limits or improve on those limits. So I'm going to start off with the Ultim Extreme. It was mentioned this morning. The main difference for the Ultim Extreme is that it's windowless. And as we saw from the previous slide, or 2 slides ago, the window material does have an effect on the absorption of those low energy X-rays. So the design focus is to run somewhere between 1 to 7 keV. It's been designed to be used with applications that are generally low beam current. We're talking hundreds of picoamps. And if you're using a standard EDS system, you're probably, my guess, you're going to be running generally at 2, 3, maybe 5 nanoamps to get a reasonable amount of counts. It's also designed to work at short working distances, which just means that you're going to be working probably around 5.5 millimeters working distance. And why you want that is that it will improve the actual image resolution of your analysis. And that will help when it comes to actually spatial resolution of your EDS. It's also designed to get that sensor very close to the sample, which will increase the solid angle. So overall, it's designed for high X-ray count rates under extremely favorable imaging conditions. And that's going to be used for beam sensitive samples like biological samples. If you're looking at polymers, you probably run into the case where the polymers would actually degrade visibly under the beam, or any other unstable materials. And as was brought up, fluorine, chlorine, there's some elements that are quite mobile in samples like minerals and in glass, things like that, where you have to just run as delicately as possible. And the last type of application is high spatial resolution. So if you're looking at nanoparticles or rods, semiconductors, or just surface analysis, if you just want to kind of analyze what's on the surface, the first 20, 30 nanometers, it's great for surface analysis. So just the breakdown of what makes it different. The electron trap is smaller. So it makes it so we can push the sensor up closer towards the sample. So this orange line here at the top here under number 1, for the extreme detector, the sensor is much closer in the probe, closer to the sample. 2, we've redesigned the sensors from round to what we call racetrack. And that's just a more efficient way to get that snout of that probe closer to the sample. Because you have a round tube, often you hit the pole piece of the microscope before you get really close to that sample. So we've overcome that by changing the shape. Probably the most important thing is we remove the window. So we remove the window from the detector, and that allows those soft X-rays to get into the sensor and be measured. We adjusted the electronics. So if we're going to be working at very low kV, we really have to push the limits of peak resolution, because down at the low energy end, there are quite a few peaks, and we have to somehow separate those peaks as well as possible so we can actually do a proper analysis. And overall, the software is designed to work with the Extreme in Aztec. And we've got other things that help protect the detector. As if you can imagine, having your sensor exposed to the atmosphere is probably not the best thing, but we have this built-in pressure sensor that will actually retract the detector and protect it behind a flap when it senses that the chamber has been vented. So if we take a look at the geometry between a standard and a regular, a standard EDS and the Ultimax, on the left-hand side, we've got a standard that kind of gives you an idea of why the geometry is much better for the Ultimax Extreme detector, because we can now get in very close to that sample, move the sample up towards the pole piece, and we get really high resolution imaging, and we can get high resolution X-ray analysis. So why do we have to lower accelerating voltages to get this high spatial resolution? So this image kind of demonstrates why we have to go to a lower energy. These are Monte Carlo simulations at different accelerating voltages, 20 to 1 kV. And that red interaction volume represents the interaction of the electrons with the sample. And you can see as you decrease the accelerating voltage, the actual interaction volume and the signal production volume for X-rays decreases as well. So to get down to, let's say, 10 nanometers resolution, we have to go to 1 kV, somewhere between 1 and 3 kV to do that. So we're going to be forced to run at low accelerating voltages. Now we're going to be penalized for going down to low accelerating voltages, because our count rate is going to fall off drastically. This is an example of what will happen if we run a sample. This is a simulation of kind of pure iron, and it just simulates the spectrum at different kVs. And you can see that at 20 kV, we're getting quite a few counts, 35,000 for the K series, 10,000 for the L series. And as we drop the accelerating voltage, all we end up with is the iron L peak to be used for the analysis. And we only get 1,000 counts per second. So it would be a very slow analysis if we were running under these sort of conditions with a standard EDS. So to get reasonable counts, we have to have a very large solid angle to increase those counts up to acceptable levels. So here's kind of our first example of the ultimate extreme. It's a pretty simple example. This is an analysis of iron oxide nanoparticles on a silicon substrate. Particles are about 14 nanometers across. The sample was analyzed in the same field using the standard EDS on the left and an extreme detector on the right. It was collected for 7 minutes at 1.5 kV at a working distance that was quite short for extreme, 3.5 millimeters. For the standard EDS, it would have had to be longer than that, just because the optimum working distance is going to be longer for a standard EDS. And as you can see, under the same amount of time, you're getting a much better map for that nanoparticle. So compare the counts for silicon over the entire map. Standard detector, 1,300 counts over the same amount of time, 60,000 counts. So that just kind of gives you an idea of the improvement over a standard detector, just because of that increased solid angle and the missing window. Another example, high spatial resolution for a semiconductor. This is NAND flash memory. And this kind of gives you kind of an overview of the improvement using a windowless detector. Now we have 3 examples at different extraneous voltages, and they're matched up with what detectors would probably be used under those extraneous voltages. So the top was collected using what we call a 100 millimeter squared sensor, which is a rather large area sensor, but we have a bigger one than that. It's 170 square millimeters. And they both do a pretty good job mapping. However, you can see that we're losing detail on this using the standard detectors. And with the extreme detector, 1.5 kV, you're starting to see features that are down to about 10 nanometers across. On the right, we have the maps and how they were processed. So we actually have a silicon map, a silicon L map, and a tungsten N map there. To get those kind of accurate distributions and clean distributions, we do process the maps using what we call a true map, which just deconvolves those overlapping peaks and removes the actual continuum or the background underneath those peaks. So we're actually just plotting the characteristic X-rays. Here's another example of where extreme would be useful. This is a biological type of sample. So this was done, I can't remember what the university was, but it was looking at hydroxyapatite implants to determine bone healing and how those implants actually help in reconstructing the bone. And it was planted into what they call mini pigs, so very small pigs. And unfortunately for these pigs, I guess they were sampled every month for 3 months. And then they were the samples were mapped and imaged to see how the implant broke down, biodegraded, and was replaced by cells and by new bone growth. So this was kind of impossible to do with TM. For one thing, these samples were rather large, and it was just difficult to sample. So they decided to use an extreme detector on a fig and then stain the sample with uranyl acetate to highlight cells that were producing new bone growth. So here's a map kind of showing what's possible. The dark blue area is plotting just nitrogen, and nitrogen is very difficult on a window detector because it's highly absorbed by the window. So having no window material in that extreme detector gives you a very intense nitrogen peak. So we get a very good indication of where this new cell growth is. It's not producing new bone, but it's new cell growth. But the cells that are producing this new bone growth are stained by uranium, and they appear as a bright green region. And the actual apatite is shown as with phosphorus, high enrichment with phosphorus. And then you also see in the apatite sample, there's yellow areas, which indicate that for some reason, phosphorus is depleted in that hydroxyapatite region, and calcium is enriched. Now, this kind of just shows an example of why sometimes a fake SEM with the extreme might be better than the TM. This is a large area map. So that's composed of 240 images montaged together automatically. And if you take a look at the scale bar, it's 1 millimeter. So that's a rather large area, impossible to do using the TEM. Another example of the extreme, more biological samples. Here we have a cryo example on the left. This, and sorry if I butcher this pronunciation, but Arabidopsis thaliana is what it's from, which I guess is some sort of cress. So this sample has been frozen and then inserted into a cryo system. So where the stage is actually frozen itself or is run at a very cold temperature. Still very delicate, and has to be analyzed using a low dose and very quickly. But under those conditions, we can still map elements and show where those elements are actually distributed without much damage to the sample. On the right, we have another biological sample. This time it's plotting the actual structures of a sample embedded in resin. And we can actually plot structures based on phosphorus and other elements. If you take a look at that sample under optical, or sorry, under I guess secondary or even backscatter, you wouldn't see those structures. You would have to use the EDS to actually see them. Now, moving over to lithium. So it's an interesting topic. Lithium detection and analysis is quite delicate for various reasons. Sample handling, of course, is one. You can't really expose these samples to atmosphere. So special equipment is required. But the windowless detector allows you to see lithium in some samples. Unfortunately, lithium X-rays are not generated in most conventional lithium battery materials today, specifically lithium metal oxides. However, there is some, the new materials coming online, such as graphite anodes or lithium sulfides, silicides, and borides. These materials seem to generate lithium X-rays more readily. So the ultimate extreme might become more important when it comes to actual lithium analysis. Now, if you want to read up about lithium analysis in using EDS, I would recommend the paper by Pierre Hovington et al. In Scanning 2016. He was the first one to actually kind of investigate this phenomenon. So it has been predicted that chemical composition plays a large part in lithium X-rays being emitted. Theoretical emissions predict that lithium metal is about 5 times more likely to be emitted as a lithium X-ray. And this is a result of electron bonding around the lithium. Now, for the oxides, transition metal oxides, there is a problem with 3 electrons. Once lithium is bonded with other light elements, such as oxygen, the 3rd electron is fully bonded, and the lithium X-ray will not be generated. So, yes, so there are some difficulties to the analysis. One of the difficulties is that the samples are very delicate, very extremely beam sensitive, so they damage quite easily. So they can't really withstand a high dose of electrons and break down during the analysis. So on the left-hand side, we see the analysis at 5 kV before it actually was done, and then after the analysis, you can actually see artifacts appearing on the surface, and those kind of bright regions are lithium oxide forming. Another example, this is an analysis at 5 kV. It's a 10-minute map at 500 picoamps beam current. 500 picoamps is actually rather gentle. And we do produce some spectra, lithium aluminate, and then we look at the lithium garnet spectra. We see a bit of a lithium peak appearing, lithium aluminate, but after the analysis, it is quite a mess. So what have we actually been mapping? We really don't know. So much beam damage at 5 kV that that map is a bit unreliable. However, if you go to 2.5 kV, remap that, take a look at the spectra. The spectra are a little bit better. You actually start seeing the lithium for the lithium aluminate popping up. And if you take a look at the mapped area after the 7 minutes at 100 picoamps at 2.5 kV, there is no obvious damage to that sample. So we should be confident that we're actually mapping the sample, not the damage. So if we take a look and just grab spectra from those different regions, and we take a look at the spectra, especially with the lithium carbonate, lithium carbonate, we can see a distinct lithium peak. We have a lithium peak popping up, lithium aluminate, but it's kind of blocked or it's hard to see because of the aluminum peak that's over top of it, but it should be there. So lithium is possible, although quite difficult to actually analyze. So now we're going to be moving over to what we call a BEX detector. And where does that name come from? It arises from the fact that it's a combined BSC detector along with an X-ray detector, hence the name BEX. Now, why was it designed? Well, it's designed for high-speed live chemical imaging in real time. It's also excellent detector for fast X-ray mapping. And if you're doing a lot of large area mapping, the term we use now kind of is cartography, it's incredibly fast. To compare it to, let's say, mapping with a standard detector, having a BEX is like having 20 of those around your chamber. So that kind of gives you an idea of how faster it would be if you had a single BEX compared to just one EDS detector. Now the applications are beam sensitive samples. Oops, sorry, I made a mistake there in my slide. So I copied the application there. So the applications will be large area mapping for one, and if you have very complex samples, like geological samples, as we've seen, and you want to do a survey. So the whole idea of BEX is to kind of get away from the traditional imaging and analysis kind of cycle where you acquire an EDS, you find an area of interest, you may do a spot analysis. It might be the area you're interested in, might not be. If it isn't, then you move the stage again, look for an area using your imaging, secondary backscatter imaging, set up your EDS, take another analysis. Is it of interest or not? So you're just kind of going through this cycle. It's kind of designed to kind of break that cycle. I guess the marketing term is the loop of suffering. So really what we want to do is do everything at once. And then we don't have that cycle. We just use the chemistry and the imaging simultaneously to find areas of interest to do our EDS or EBSD or WDS analysis. So for imaging, you can use the secondary electron detector. So it detects low SEs, 50 eV. It's near the surface and it provides topographical information. More times than not, if we're interested in chemical analysis, we want to use a backscatter to actually help us find areas of interest. So it's composed of high energy electrons, backscatters. They originate deeper in the sample itself. They provide some sort of information about the average atomic number. And we can actually use different sectors in the BSC to actually get some topography, some information about the height of the sample. So what we've done is combined the backscatter along with the X-ray. And if we combine both, we get a little bit more information in real time about our sample. So as you can see that with just the backscatter alone, there was actually a rather unique particle in that sample, one that was maybe a little bit more enriched in silicon than the others. So it combines BSC X-ray signals and it can be acquired simultaneously. Another important factor is it works under conditions for traditional imaging. So you don't really have to increase the beam current and make your image soft. You can run it around 2 nanoamps and it's running at as fast as it can, around 2 nanoamps. So that's the kind of design of it. It's a detector. It's a flat detector that if you insert it, it goes underneath the pole piece. So if you're familiar with the backscatter, a regular backscatter detector, it's in that position. It's retractable. And it's really useful. So you can do just regular backscatter imaging if you want, or you can use the EDS detectors at the same time. Backscatter imaging is very good. One of the reasons is that the sensor head is Peltier cooled, so that increases the sensitivity of the backscatter detector. And the X-ray sensors are large, and because you have two sensors, each sensor is going to have its own digital pulse processor. Essentially, it's going to have its own pipeline, so you can actually have a very high throughput. You don't have that kind of limitation of having just one digital pulse processor. Now, one key point is it works alongside a conventional EDS. You cannot purchase a BEX detector by itself. It requires a regular EDS. And the reason for that is a regular EDS is going to be used for the low energy end. Now, you can imagine that because that head is so thin, there is no space to actually put in an electron trap like we have for a regular EDS detector. Instead, we use filters that block the electrons coming off the sample so they don't enter into the sensors. So to do that, we sacrifice the low energy end from the BEX, but because we have a regular EDS detector, we can capture the low end using the standard EDS. And a standard detector is used for auto identification, quantification, and just light element detection. So just to give you a kind of an idea of its performance. So this is what we call, this is a special BEX navigator, but if you're familiar with live chemical imaging in the regular part of Aztec, it's very similar. There's some improvements to it. But with this, you can see that we're getting all the information possible from our sample, and we can find areas of interest to do further analysis. And once we've found an area, we press the capture button, and then we have a permanent map, permanent acquisition, and that's automatically stored into the project. So it's designed for kind of daily imaging, optimized for normal imaging conditions below 20 kV, 1 nanoamp to 2 nanoamps typically. Flexible working distance, so optimal working distance is 8.5, but anything greater than 6 millimeters, it can be used. And of course, if you want to go to a longer working distance, that means you're getting a bigger field of view, so you can map quite large areas. Right, and if you have a detector that actually has a wide field mode, like a test scan, and I think probably some Zeisses have those, you can go into wide field mode and actually map that. There's no shadowing, and you really don't appreciate this until you actually use it on rough samples, where the chemistry gets quite confusing if you're using a regular EDS at a takeoff angle of 30 or 35 degrees. The shadowing makes interpretation of maps quite difficult. But because of the position of the detector underneath the pull piece, it really isn't a problem. Flat tube, so we really have a very flat tube here. So no chance of you kind of running into other things in your chamber. And here's just the actual head itself. Because it's under here, you just like a regular backscatter detector, if you hit it, it might be damaged, but we could easily replace that head for approximately the same price as just a regular backscatter. BEX is also useful for fast mapping. So this is a geological sample. And if you take a look onto the right, it kind of gives you the description of it. So that's a 2K by 2K image, very high resolution map, run at 20 kV, 2 nanoamps, and that took 15 seconds. So you can imagine if you're going to try and map something that's measured in square centimeters, being able to collect that's a 500 microns, so that's about a millimeter by a millimeter. In 15 seconds, your large area maps are going to be collected very quickly. So here's an example of a stub filled with particles. This is collected, mapped in 30 minutes. That's 100 square millimeter stub covered. Electron image, high resolution, 1.3 microns. That's 88 million pixels. The X-ray maps were 2.7 microns resolution. That's 21 megapixels. And after 30 minutes, you've got so much detail, you can zoom in to one particular field of view, and you have quite a bit of detail. So lots of data can be collected very quickly. Now, because it's so fast, we've kind of improved our large area mapping routines. So now it's quite simple. You can just highlight a particular registered image. It's here we can see that we're just kind of drawing a square there, which creates a field of view. And then once that's done, automatically you start just mapping your area. Now this is sped up 60 times, so it's not this fast, but it's collected from the previous samples. That was about 30 minutes. Okay, so quite easy to create large area maps now. So we're kind of moving towards like surveying the whole sample before you actually start picking out places to do a more intense analysis. That's kind of where we're heading, and collecting lots of data so you can make it almost like a virtual sample, which you can take off and then do your processing offline. Now, just to point out the quality of the backscatter, which could be kind of important, because in a way you could replace your backscatter detector with this, and you want to make sure that your backscatter is very sensitive. So if we take a look at images here, raised joint, and we've got some ECCI imaging from a steel, beautiful images, and that those are achieved just because we Peltier cool the backscatter detector. You still have some flexibility. For instance, you can still go into topo mode and to turn off segments to the detector to get different sort of topographical effects. So in summary, EDS detectors are not built the same. There's quite a diverse range of detectors optimized for certain applications. If you have a particular application, you should probably select a detector that's optimized for that. So for beam sensitive samples, or if you're really interested in high spatial resolution, you probably should go with larger sensor detectors, especially windowless detectors. Chemically complex heterogeneous phases, you should probably use something like a BEX detector, high throughput. And it seems that the future trend for EDS is going to be more towards live chemical imaging and more of a quick survey approach to sample analysis. So that's going to be probably what you're going to be seeing more in the future. Thank you. Any questions?
Again for your talk. I'll be moderating the questions again. So we have, and as a reminder, please put any questions into the Q&A section at the bottom of your screen. So the first question that we have here is, can the Ultim Extreme, similar to other EDS detectors, be configured spatially to work with simultaneous EBSD?
So we don't have any systems with the Ultim Extreme with an EBSD system. I would probably say no. I mean, probably in some configurations we could, but generally EDS, a regular standard EDS, comes along with the EBSD.
Gotcha. Okay. Thank you very much for your answer. Still waiting on a couple of questions. I can give it another minute or so in case people are typing, but please be sure to put them in the Q&A section. I guess I kind of have one question. Oh, there's one more. Perfect here. So why do the K series counts drop off with a low voltage faster than the L series?
The over voltage was kind of mentioned in the first talk. So as you go to lower external voltage, and the over voltage gets lower, then the intensity and the probability of an X-ray being generated decreases. So with L peaks, which are lower energy, the over voltage is always going to be rather high until you get to quite low external voltages.
Gotcha. Thank you. So one question that I have is that I work with very porous materials. So I was wondering if either of these detectors are a little bit better with things that have very high porosity as well.
Okay, that's an interesting question. The way I would approach it, I guess, is can you define the size of the pores? Is there any way to do that? And I would probably map, to be honest, I would map the sample and look at the intensities, and then go for the areas that have the highest intensity of a particular element. And those should be the regions that don't have pores below the surface. That would be probably my approach.
Gotcha. Okay, that makes a lot of sense. Thank you. Okay, we have one more question, and please keep sending in your questions as well. We have a bit of time. So the question is, does Aztec have tools for metrology on the BEX images, like particle analysis?
So we do have a particle analysis software, automated particle analysis software that works with regular EDS detectors. It sounds like BEX will eventually be able to work with that software, but it can't now.
Great. Okay, thank you.
All right. Well, if we don't have any more questions, we can wrap up this morning. Thank you, Richard, and big shout out to Kelly. Thank you, Kelly, for participating and helping out with the questions. Oh, and just Richard, yep, just stop your screen share and then the talks will start again at the same time tomorrow morning. We'll talk about EBSD, so make sure to tune in for that. If you have a work or a demo here at Nuance this afternoon, make sure you look at the schedule again and reach out to me if you have any questions about where you should be and when. But thank you all for attending, and hopefully we'll see you again tomorrow. I'm Tirza Abbott. I manage the SEM facility here at the Nuance Center at Northwestern University, and welcome back to those who are joining us for day 2 of our workshop with Oxford Instruments Nano-Analysis on elemental and structural analysis in the SEM. And today we're going to be focusing on one of my favorite electron microscopy techniques, electron backscatter diffraction, or EBSD. And if you're familiar with EBSD, then you will almost certainly have come across our first speaker of the day, Dr. Ben Britton. Ben is an associate professor in materials engineering at the University of British Columbia in Vancouver, Canada. He's been using EBSD for 17 years, starting his career with an Oxford Instruments Inca Crystal EBSD system across the pond of the UK. He's used detectors from the 3 major manufacturers and has developed open source analysis approaches, as well as the high resolution electron backscatter diffraction technique with his PhD advisor, Dr. Angus Wilkinson. In addition to all of this amazing microscopy, Ben is also involved in a number of efforts to make STEM a more welcoming place for people of all backgrounds. And I am very excited to have him here today. So without further ado, I'd like to turn it over to Ben Britton.
Thank you very much for the kind invitation and introduction. So let me get, where's the fun bits? Sort the laser pointer out, which I can't. There we go. Right. Yeah, so I'm going to talk a little bit about advancing EBSD and transmission Kikuchi diffraction. And I had the ambitious title of new algorithms, more dimensions, and new detectors. So we'll see where we get to. I'm basically the presenter who sells the work and other bits and pieces. There are significant contributions from a number of people, some of whom are in the audience. There's a group at the University of British Columbia who I work with, as well as a number of folks, Tammy gets 2 mentions, but a number of people at the Imperial College London. And then we also have some good collaborations with TESCAN and growing the links as we progress. The work requires funding, so there's also significant contributions from financial for setting up the problems and also providing funds for students and staff, etc. And so I acknowledge those as well. So I recognize that many of you have different backgrounds and I just don't want to lose people. So let's just do a little bit of the basics of EBSD. I'm going to do a soft plug. If you're interested in EBSD, perhaps one of the ways that you may have heard of me is by popping onto YouTube. There's a series of lectures that go through the different bits of the technique and give you some basic ideas about how it can be used and interpreted and other bits. Importantly, the slides are also available, and I'm looking to add some more in due course, but time is difficult to find sometimes. But the basics of the EBSD technique is that we introduce an electron-focused electron probe in the scanning electron microscope. And then we also introduce a camera, and there are a variety of different cameras available, different geometries and setups. In the conventional sort of reflection EBSD mode, the camera is inserted to the sides, and the electrons go into the sample, and as they go into the sample, they scatter, and some of those scattered electrons lightly scatter due to phonon interactions, and then they escape the sample, and they produce these beautiful diffraction patterns. So the diffraction patterns contain a number of features that are interesting. So first and foremost, we have the so-called Kikuchi lines, which are effectively two conic sections that are separated by an angle 2 theta and correspond to the specific diffracting lattice planes. Each of these diffracting lattice planes, they intersect at a zone axis, which is a crystal direction. And so one of the nice things about this is that the EBSD technique is done in direct space, and that can be helpful for various bits and pieces. We have some geometry that's important. So we have the pattern center, which is the shortest distance between the detector and the interaction volume. And that sets up how much the Kikuchi pattern subtends. And one of the major strengths of the technique is that we get a very large angle subtended. In short, that means we see a lot of the unit cell. And that makes it easy because we now have more than one zone axis present. And so that means identification of the crystal orientation is much simpler. Those of you who might be familiar with Kikuchi pattern analysis for thick crystals in the TEM probably spend a lot of time using them as sort of roads to find out where the crystal is oriented. But you'll only be looking at a small, narrow view in the TEM. When we do this, we can do it in a rapidly automated manner. So the combined efforts of lots of people has been created some commercial software and open source tools that enable us now to index and represent this data. This is just a nice example. This is from Jim Hickey's work, but it really just shows us some simple bits of the technique. So this is a rolled interstitial free steel, and this particular microstructure condition gives us a strong texture, where we see in this strong texture, the 111 crystal axis is pointing out of the page. So we can represent it. This is with the little cubes presented, or we can represent it in color maps, the inverse pole figure maps. Again, I'm not going to go into too much detail of what these represent here, but we can effectively encode the crystallographic orientation, and we'll see a bit later as well the crystal phase and a few other bits and pieces. So it's very powerful. This can be done across a range of length scales, and you're going to see a few of those examples from our system at the University of British Columbia. So the sort of simplistic bits of the EBSD technique is we capture a diffraction pattern on our screen. This is what the screen shows, and this pattern is directly encoded to the crystal orientation. So as the crystal rotates, the pattern moves across the screen. And that is, again, basically we then interpret this pattern automated to get the crystal orientations. So just a few examples from our test scan PFib with our Oxford Instruments Symmetry S2 detector, and this is largely the work of Ruth Birch in here. So our system at the University of British Columbia, which we are almost finished commissioning, it includes an SEM, which we're looking down, and then we have a fib column that's at an angle about 52 degrees, I think, off the column. And then we have a nice setup in the test scan instrument where we have the EBSD presented at a slight angle, but we'll see that's very useful later because it enables us to do static three-dimensional analysis where we do not move the sample between slicing and EBSD. We also have a large EDS detector, so we have the Ultimax 170, and that's, again, to enable high throughput. And then we have significant numbers of other detectors, depending on what we want to do. So we have a STEM detector and 3 backscatter detectors, amongst other things in this. So some of the data is collected from training, and some of it's now online. This is now new data in the one that we're going to show in a second. Here's decided he wants to eat things. Anyway, hopefully it's not too noisy. So this is a large map of steel that we've collected. What's very cool with the Symmetry S2 detector is that it can be operated very quickly. And the data that's sort of online analyzed was captured in about 1 hour and 22 minutes. And this data set contains 17 million data points. So we have 17 million measurements, many of which have been successful to reveal the microstructure. And that's what you see in these 3 corners over here. What's really nice, and you'll see in the next lecture, Mike will talk you through MapSweeper and pattern matching. We can take this data set and we can analyze it offline. This is just to show the sort of improvements that you can get from this microstructure analysis technique. This significantly improves for poor quality patterns towards interfaces, And this is very important when we're looking at the different alpha laths that are present in this microstructure, where we're going to be interested in specifically the parent austenite grain structure of this steel. Takes a little bit of time, but this is offline, so we just have a computer that sort of churns through data as we want to in there. But it's very, very powerful to improve the indexing. And again, I just stress this was collected in 1 hour and 22 minutes. Ruth Birch is a wizard at getting this to operate really nicely. We also have done some large area mapping depending on the camera setup, just to highlight. This is an example from Shuhang Li and Ruth Birch looking at a magnesium sample, so quite a tricky sample system to work with. With pretty good sample preparation across a large area, we're now extending a 5mm by 5mm low magnification method. Excuse me 1 second. Apologies, my puppy decided he didn't like microscopy. So this is a large area map that's presented. It's 5mm and it's just really nice. So we can then choose. So this is looking at roll texture, but specifically here we might want to look for a particular grain orientation of interest that we'll see a bit later is particularly important for our studies of the deformation mechanisms of magnesium here. Again, map sweeper. This is not a cleanup routine. This is just a different way to index. And this shows that we can now recover the microstructure really beautifully across this whole domain. We can also do three-dimensional analysis, and we'll see this a bit later, but by serial effectively ablating or removing the surface using the focused ion beam instrument. In a plasma pit, we can do this relatively quickly. Here we have a slice thickness of 100 nanometers, a step size of the EBSD data of 100 nanometers, which recovers a voxel size of 100 nanometers. So we have three-dimensional pixels, the voxels, and this is presented with respect to the IPFZ. This is a vast steel sample, and so we can see the slice and wipe type visualization that shows us the microstructure, and you can imagine the sort of problems that we're interested in. What are the interfaces that are present, and how do they represent themselves in 3 dimensions? This is a relatively small data set that's behaving itself. We're getting up to sort of 250 to 500 micrometer volumes, which is really starting to be powerful for our steels microstructure problems. We can also use the instrument to do transmission Kikuchi diffraction, and specifically we can do the lift out to make the TEM foil with a uniform thickness all in the same instrument, and then switch it over and put it in the TKD. This is using a symmetry detector, and as I say, we have a STEM detector on the instrument as well. So the STEM detector, effectively, we have a diode that presents itself below the beam. We have a thin transparent foil in the SEM at relatively low voltages for TEM type work, and then we're measuring the signal as we move the beam across the surface. There's some small noise issues in our instruments, so we just need to we'll get this a bit better as we get the instrument fully commissioned, but we can start to see the complementary nature between the bright field, dark field, and HALEF STEM, and the associated EBSD analysis, or TKD more formally. What's particularly interesting in this material, we're interested in very fine pockets of retained austenite because we want to know about the processing conditions. So this is a 20 nanometer step size. We can go a bit finer if we want to. But what's very cool is that we can confirm that we have pockets of very, very small austenitic regions. And we can do this by directly looking at the transmission Kikuchi diffraction patterns. So the regions that we have here, we have the red that shows the ferritic regions, and we can confirm that they're ferrite TKD patterns. And then we can see, and we can use the software to help us on this seeing process in an automated manner. We can see effectively the austenitic is a very different crystal structure due to the intensities in other bits. But what's particularly cool in here is we can see also directly that these different ferritic laths and the associated austenite grains, they have some overlap. So we can see common bands and poles, which are associated with all of the orientation relationships. And this tells us again about the crystallographic processing, thermomechanical processing of this steel, and hopefully the properties of that steel. So that gives you just a little bit of flavor of some capabilities. Now I want to show you sort of how we've been pushing the technique significantly further. And I have sort of 4 topic areas that I hope to get through, subject to time. But I want to show you a little bit about learning more with machine learning. I want to talk about some new imaging modalities that we're opening up, some new hardware opportunities, and then some 3-dimensional analysis of some magnesium indents in here. So the first piece is using posh statistics, machine learning, to enhance robust EDS and EBSD. I believe yesterday there was a great talk from Jennifer on EDS and WDS, so this overlaps nicely with this. Here we're going to basically just switch on the EDS detector at the same time as our EBSD, and we're going to collect pretty good but not idealized EDS data and use that to enhance our ability to see inside microstructures. So we know from the energy dispersive X-ray spectroscopy that we can produce a characteristic energy spectra where we have the number of counts of our different peaks, our different elements, and then across X we have the energy that's quantized based upon the detector. This, if we think in a microstructure, due to the size of the interaction volume and a few other bits and pieces, this will be of a larger volume and may have poorer spatial resolution than the EBSD technique, which tends to be confined, associated with the small phonon scattering volume for EBSD. If we have our EBSD data, we can start to see that we can match according to the crystal structure, i.e. the phase, but we can't get the chemistry of that. And sometimes there are some complications that this can move relatively quickly due to the crystal orientations shifting and moving us around on the patterns. If we just do conventional analysis and you switch between the two modalities on the microscope, this is not an Oxford instrument system for this setup, but we can see that we have the band contrast type maps or image quality that's presented on the left. We have the conventional EBSD where we've just put in the Hopf-based indexing, a very traditional method to identify the crystal phases. And we start to see actually there's a huge amount of, say, uncertainty with this precipitate where it's being labeled across multiple different ones. And we can see it's got some, noise points. I'm not sure what's going on in here. On the right-hand frame, we can see the energy dispersive X-ray spectroscopy data, and we start to see this is relatively blurred, recognizing this is quite a small step size. So these are relatively blurred, and we can just sort of see that this is a molybdenum tungsten-rich region, but we would imagine that this is sort of bleeding from the neighborhood associated with that convolution due to the large interaction volume. So the question I, as a naive supervisor, said to Tom is, could we put these two data sets together and enable us through some software-based approaches to improve the spatial resolution? So importantly, there's a significant difference in the interaction volume of these two techniques. So the EDS signal volume is related to the slowing down of the electron beam associated with the continual scattering, and then we get X-ray generation, escape, and detection to give us the signal that we'd like. So the typical sort of quant volume is typically large, 1 micrometer or more, depending on what you've done, depending on the material system as well. But the qualitative information, does this have more tungsten or less tungsten in the neighborhood, can be, if we're very careful, from a smaller volume. The EBSD signal, typically it's a much more confined volume associated with dynamical scattering events that give you small point sources in the material. And we get diffuse scattering, the background in the pattern that gives from a larger volume. So the EBSD signal that we care about to classify the data is typically quite small, and that gives us something of the order of 20 by 60 by 20 nanometers, so much more confined. But we also have some statistical differences associated with the signals, because the EDS signal has this background or bremsstrahlung radiation with a few characteristic peaks that are superimposed, and it's relatively smoothly varying. So there's not strong statistical variation between, say, different grains in our material. We sometimes get step changes if the material has decomposed to give you two different phases in a local region. But we also have some statistical challenges because nature's not nice to us and there's significant peak overlap in our spectrum. And this is especially important for lower energy analyses. We might like to use lower energies because that would improve our spatial resolution in the EDS technique. This is a one-dimensional spectra, and there's actually a limited amount of information contained with it. It's still very useful, but limited compared to the number of signals in the EBSD data, because our cameras are typically, say, a megapixel with 1 million data points per diffraction pattern. The EBSD signal is very useful if you have good patterns, and I can spend far too long talking about sample prep. We have strongly varying signals because there's sort of dependence on the crystal orientation and phase and some other details. And there's lots of signal per pattern. So we've got in this particular setup, we have a Brooker system that we used, and it has a 2 megapixel camera. But just note across the map, of course, that data is not unique because there are many different grains that could be the same orientation, for instance. So we have some strong changes in this data, strong changes in phase, and limited changes in the chemical variation. And that's why we get that mess in the Huff-based indexing. So one of the methods we sort of started to think about is, could we use some statistical clustering techniques? Any of you who are familiar with these approaches are probably familiar with the principal component analysis method. So the principal component analysis is an eigenvalue, eigenvector decomposition. And effectively what it does is it clusters, it's a non-spatial clustering of data to enable you to reduce this map, which contains a series of diffraction patterns, so P by Q pixel diffraction patterns, collected at n by n points across this map. We can take this, and if we effectively convert this 4-dimensional data set into a 2-dimensional data set, where we now have the diffraction patterns running as vertical columns and the points running as horizontal rows, we can now effectively do this decomposition to give you the principal components. It's an orthogonal basis eigenvalue, eigenvector problem to give you the principal components. The strongest principal components is basically the mean of this data. The second is something that is strongly varying from that mean. Specifically, it has this orthogonal quality in there. And then at every single point in the map, we can have a score which tells us how does this principal component relate to this particular point. Now, Angus Wilkinson and his group did a really nice trick in that they took the principal component analysis and they used another statistical method called multivariate statistics, MSA. And that multivariate statistics, you can take the first for this data set. We recognize there are perhaps 10 grains. Let's just be cautious and say there are 30 distinct signals, and we can reduce, therefore, the number of principal components for the first 30 that are interesting. Now, we recognize that each of these diffraction patterns should have the same variance associated with each of the patterns if it's a physical signal, i.e. the contrast in brightness is uniform across this map. So we can take the 30 signals and we can rotate the basis vectors, and we get effectively 30 uniform variants, and that enables us to get this beautiful map where we now have effectively a diffraction pattern that is the sum of this domain. So this blue domain is the sum, so we get a huge amount of dose, signal to noise for that particular region. And this score map looks a bit of a mess. It looks kind of like our microstructure. This is kind of a backscatter type image. It looks like our microstructure, but we see, for instance, there are multiple regions with common diffraction patterns, although they're just shifted. They're shifted by at least a pixel, so they look significantly different to our statistics. Fortunately, however, we can then take this 30 signal data set of the diffraction patterns and then use pattern matching to identify the crystal orientation and phase. So we've converted effectively 9,032 diffraction patterns to 30 problems where we have to solve the crystal structure. And those 30 problems have a very high signal to noise. When we do this, we can then label this according to the crystal orientation and phase. Here's just the orientation as shown as the IPF data. And we see the grain structure is now recovered. We see there are sort of low angle grain boundaries associated with the shifting from one domain to the neighbor. So that's just an artifact of the algorithm. But this has made this problem much easier to work with. And you'll see this is going to be important in a second. So my naive comment to Tom was, well, let's just throw some EDS on the top of it. So we have this same data matrix that contains the diffraction patterns, and now we add in the EDS data. So we now add the column of EDS data on the bottom. If we do some appropriate statistical normalizing based upon the number of observations, then we can compress this properly. And then we can say, so every single point has an associated characteristic pattern, an associated EDS spectra. We have the individual vector that's present, and we do the PCA and MSA as before. Now, the important detail to recognize is that as we do this, we want to worry about the balance of signal between the EDS and EBSD. So we can think about this in terms of having a small weighting function, W, that says how much EDS signal is present. What we think about is that the PCA is trying to find unique clusters in a data set. So if we just think of this sort of simplistic problem where we have 3 different measurements of properties, and the EDS signal is, for instance, variable 3. So the W, the weighting function, stretches this axis up and down. And all we're trying to do is find unique clusters and then describe that cluster by the centroid of the cluster. So if I increase the EDS signal, I'll get a strong separation based upon the EDS characteristic X-rays. If I reduce the EDS signal, my characteristic separation is going to be more described by the EBSD patterns. So Tom worked hard to find effectively an independent of a human method to select an appropriate weighting function, and that's described in the paper, which is also available in the archive. So we have this. This is the description of that weighting term. So if we're EBSD weighted, we can start to see actually the spatial resolution becomes quite nice to show the crystal phases. So we've done the PCA, we've then done the MSA. So we've done the two statistical methods, then we've pattern matched for the crystal phase, and we pattern matched against the cobalt, the MC carbide and the M6C carbide. And we can start to see it's really nice in this microstructure. We can see some fine scale precipitates on this sort of grain boundary. Here's the grain boundary in IPF space. And we can see these different precipitates. Due to memory requirements, we had to do this in a sort of Warhol-like tile. So each of these tiles is operated independently. And we can see that the EBSD weighting gives you a strong spatial resolution. The EDS weighting suppresses these small features. So you have to choose the appropriate range to get it to behave itself to show the crystal structures and phases out properly in the microstructure. Again, this is not human chosen for this value in practice. The computer does it for you. I'm just showing this for illustration. Once you've done this, you can take each of the characteristic signals that have been ascribed to the different crystal structures and then effectively quant either the direct sum EDS data or the reduced refined component data sets. And we can present this as a radar plot to show the different chemistries of the different phases. This is very, very useful. We actually use this to help design a new alloy system. And so there's another paper that Tom worked on to design a whole new nickel superalloy based upon this approach being used. It was used to study, I think, 30 different alloys. And that's sort of how the algorithm is easy to use in that way. So that's some statistics where we're linking the two techniques together. We can now look at developing a new image mode. So this is, again, just using a conventional detector, but we're going to use our statistics to help us on this. And this was, again, work within Tom's PhD. So the problem we're looking at is, again, in the nickel system. So in the nickel system, for superalloys, for aerospace applications, we're particularly interested in the ratio and spatial distribution of the gamma prime phase within the gamma matrix. So we effectively have an ordered superlattice where we have an L12 structure where the nickel site sits at Ni3Al, the nickel sites sit in the face-centered cubic face-centered positions, and the aluminum sits on the corners. In the disordered matrix, there is effectively no ordering, and so we can swap those atoms around. Now, conventionally, to identify these, you'd either have to go into the TEM and use the superlattice reflections to identify those crystal structures, or if you want to see across large regions, you would etch the microstructure. Now, again, if you're doing an alloy design study, the etching depends on the chemistry. It's a very artisanal approach, anyone who's done really careful etching, because you want to make sure that you're not removing too much of one phase over the other, especially if you're going to do area fraction analysis. And this is just showing effectively different cooling rates to show that we can control the ratio of, say, primary large gamma prime to tertiary, the very fine scale gamma prime that's present here. So we asked ourselves, could we use EBSD to classify and understand those crystal structures and phases? So if we just do conventional EBSD, we can see the image quality data doesn't show anything too interesting. You can start to see perhaps a periodic structure appearing, but it's really asking you quite a lot to believe that that's the different microstructural regions. Because these two crystal structures look the same, you can just put the FCC phase and it will index them both happily. You'll get a single map that's shown and the diffraction patterns don't vary very strongly. If we then look at the crystal diffraction pattern, so this is the diffraction pattern presented as a stereogram, as a simulation, and I'm just flickering between the two crystals, we can see there are subtle variations. Certain bands are disappearing and reappearing. On the right hand, we have what's called the spherical radon transform. The long and short of this is if I take this, say, the North Pole, this circular peak at the center, the structure of this peak is described by the equatorial domain in the pattern. So the radius of this is related to the band width, and the intensity is related to the scattering of that particular band. And so I can just look, and it's the perpendicular sort of great circle is described by this structure. So this tells me this is a specific crystal plane that's of interest. And again, we have open source algorithms that will do this transformation if you so wish. So we applied Tom loved his statistics and machine learning. He now earns a lot more money than me in a quant in a bank or a hedge fund, I think it is. We now use the statistics. We use 3 different methods because we could. So the PCA, this is the method I've described previously. There's a method that's used in HyperSpy for EDS called the non-negative matrix factorization method. And there's another method that's useful in other domains called the autoencoder. You basically have a compression and a decompression, and you reduce this down to the simplest components that we call the latents are present in here. So each of these give you sort of factors and scores, so the diffraction patterns and where the diffraction patterns are found across the data. So if we do this decomposition, I'm just going to show you the PCA approach. We can look at the PCA variables and we see PCA, each of the different components, and we can see how the scores, how they're spatially distributed. And what's particularly cool here is we can start to see that gamma-gamma prime structure appearing. If we choose the appropriate components and scores, we can then say, actually, we think, for instance, in score 1, this represents the bright colors score towards the matrix, the dark colors score towards the gamma prime, and vice versa, I think, for this one, similar for this one. And then we can combine those two and we can give you a description of the spatial distribution as recovered from the PCA approach of the gamma prime in the gamma matrix. And hopefully you could then see we could quantify the size distribution, etc., of those precipitates in this material with 50 nanometer spatial resolution, so finer than 50 nanometer spatial resolution. So we're really pushing the EBSD technique with a conventional setup here really nicely. The other thing we can do is now we have the tools to do this spherical transformation. We can take the diffraction pattern, we can project it on the surface of the sphere, we can infer the planes, and then we can sum along the planes. This was described in some work I did with Ralph Hjelmstad, who developed the MTech technique. So we can sum across each of the different crystal planes and give you the band profile. So if we look at the band profiles associated with this, we can look at the experiments and the simulations for the particular crystal chemistry, and we can start to see there are strong differences, or subtle differences, sorry, should I say, between effectively the matrix and the precipitate. Specifically in this cobalt-based nickel superalloy, there is a doping. So the tungsten, for instance, heavily doped, I think, on the L12 structure in here. So we can start to see there's some variations. But what's kind of neat is that then we could perhaps look at a reconstructed map based upon the intensity on this Bragg peak. So if we reconstruct this map, we can see the reconstruction of the 100 crystal plane families, the reconstruction of the 111. We sum effectively the total intensity within twice the Bragg angle, and we can start to see these spatial maps really start to beautifully show that the gamma-gamma prime is revealed with exquisite spatial resolution. Again, recognizing the length scale is about 50 nanometers in this little bit is really good, but we see some peaks where there is effectively an invisibility of those two different crystal structures. And so this is a new form of imaging that's well set up for this sort of single crystal nickel superalloy analysis here. These codes are all open source, the video is recorded, etc., but you can have a look and pull the codes, and we're excited to see people using this in anger as well. So this is now moves us on to the sort of new hardware piece, and this is a large amount of work by Tianbi Zhang and Alex Foden, and they've been, well, Alex did a little bit in his PhD and he's now finished. Tianbi is doing a huge amount of work of this now at the University of British Columbia, and we're particularly interested in, can we develop new hardware to enable us to push EBSD even further? So new detectors, many of you are familiar that there are direct electron detectors, specifically the area that I'm going to look at are the MEDIPIX and TIMEPIX based detectors. These pixelated detectors, they can be very useful because they improve the signal to noise even further than indirect. To be specific on my language here, an indirect detector is like the symmetry detector where we have a phosphorus insulator, we have an optical coupling, it's a fiber optic bundle, and then that brings it to in the symmetry, it's a CMOS fast detector. In a direct detector, we don't go from light to electrons. Instead, we just have electrons being counted. And specifically, these were generated as particle detectors for the CERN consortium. So there are multiple detectors, some of which are commercially implemented, some of which are in development. I happen to buy a few of some specific things, and I'm going to show specifically TIMEPIX 2 and 3 detectors the form factor is one of the important aspects that we like for this particular holding. So our one setup is we can do a reflection-based method. One of my favorite materials is silicon to show off EBSD stuff. So here's a simulation, here's an experiment, and here's the difference. What's super interesting about this is 256 pixels by 256 pixels. So it's actually a very small amount of information, but it has very high acuity, effectively high angular resolution within the diffraction pattern. And if we set this up badly in some regards, but we have the pattern center and detector in a poor position, we can start to see some physics of the scattering. Broadly speaking, the electrons that hit the bottom of the detector have scattered further in the sample. And that changes the brightness and contrast along the band. You can see this as you zoom along here. You can see there's a cool change in the band width and the intensity because the energy of the electron transport inside the sample has changed. We can use this to do sort of new, although this was described a very long time ago, but we can effectively take this diffraction pattern, we can put it on our sphere and we can inflate it. And so we can effectively just apply the symmetry operators of our crystal to start describing the entire diffraction sphere. In this particular case, just when I set this up, I'm actually missing one zone axis, so I can't inflate it fully to describe you the full case. That's just because I wasn't thinking when I did this, but it's pretty cool. So we can see the acuity is really good. So this is the raw event data. This is that Hjelmstad's collected. And this is the FFT data. We have the simulation. If we just do a background correction and a few other bits, we can see that the FFT, which tells us the spatial frequencies, goes out very far. In an indirect detector, it would go out towards here. So we get probably a factor of 2 plus of what's called the modulation transfer function, or the detector quantum efficiency associated with this detector. And that's super cool because it enables us to see very fine features. Specifically, we can start to see that there's a fine band edge that's presented here. We can see the cross-section associated with this little dimple. And these crossing points, if anyone has done seabed-based TEM imaging, those crossing points can be super useful for lattice parameter assessment or energy and other bits and pieces in there. So that's why I like that. So that's sort of taking the reflection geometry. We then asked, could we do something different for STEM in SEM? So there's some really nice work from a French group developed this originally, and then it's been commercialized by Brooker. But effectively, they took a conventional EBSD detector and they put a mirror. So they put a mirror here and they put the phosphor, and they put the phosphor so it presents underneath the sample. If you do this, you now have something that looks like a 10, except of course it now has a relatively short camera length, so it's wide angle. This is different to the TKD that I've shown you previously, but we have the off-axis, which still works really nicely. But we can start to see that in the off-axis configuration, very similar to what previously shown, we have a significant divergence of the bands because of the way the hyperbolic geometry is set up for the Kossel cones. In here, we start to see the direct beams presented, and so the angle is a bit easier to understand. But we can also see some cool stuff associated with diffraction spots and other features. So there's some benefits, as well as the total electron yield for the scattering forwards can be very helpful. So Hjelmstad started and got working really well on this, and has developed effectively a stage that goes inside a couple of different microscopes. It fits in the palm of your hand. And this whole stage has a XYZ stage to move the sample around. We have the detector in a closed configuration here. This is the small form factor I mentioned. And we have a USB readout that then goes out of the vacuum. What's nice here is that we have a relatively flexibility of the sample to pole piece, so the working distance that we're working at, as well as the sample to detector. So we can change the camera length quite flexibly as well. And so we now have the primary beam that goes through our electron transparent foil. And then we have the transmitted beam directly inside the pattern, and we have the scattered beam coming off at a scattered angle. If we do this carefully, and this is where Hjelmstad's worked quite hard, we can effectively do like your iPhone or other device does for a night photo. It does a high dynamic range where it takes multiple pictures, very short succession, but with different exposure times. And then it will software compress that to reproduce an image that effectively deals with regions that are saturated, too bright, and regions that are underexposed. So the underexposed regions, it will grab from the longer duration, and the saturated regions will be grabbed from the shorter duration. So Hjelmstad went away, collected this data, so we hold the beam constant at one point, We grab effectively 4 shots. It takes, well, for an individual frame, it will take about 0.12 seconds. So we can get about 10 hertz for this particular setup. Our readout is a bit limited. This is also with, I think it's 400 picoamps of probe current. So just note, conventional TKD is probably running at 1 to 10 nanoamps of probe. So we're in a different domain of the events for lots of good reasons. So we can then take this data, we flatten it because we can work out the profile. So we do an angular sum, so a radial sort of angular sum of this, work out the profile. We can compress the profile based upon the total exposure time. We can get the reference curve, and then we can divide the experimental data by the reference curve, which gives us our flattened data. And what's super nice about this is it enables us to access very large camera angles. So we can go up to 55 degrees from the primary beam. We can probably go a bit further, I think, and we can go pretty close. So we can see effectively the Kikuchi pattern is produced less than, say, 5 degrees from the primary beam, and we see the spot pattern for this particular example. Why is this useful? If you want to understand the unit cell in a crystal, if you're in the TEM, because you're only seeing perhaps 5 degrees, you have to need to shoot along 2 different zone axes to work out the length of A, B, and C, and the angles alpha, beta, gamma. In here, we're now seeing effectively the whole crystal in one shot. And that's particularly powerful if we want to work out the structure of that material. And we have what's really nice, we have the spot and the diffraction pattern to work with, depending on our analysis approach. So this is just talking you through the sort of bits and pieces. What's also super nice is that this flattened fused on-axis TKD pattern now has a uniform contrast that looks like a conventional EBSD pattern. A very beautiful one, but a conventional EBSD pattern. And so it's trivial for us to do a half transform and identify the peaks and index it. We can also simulate the diffraction pattern to show this, and we can show it has high spatial frequencies recovered. So it's really beautiful for here. So that's kind of helpful. But what was kind of fun is that we can also do that similar inflation on the sphere. I'm just showing it in a stereographic projection. If we look at this is an aluminum crystal that we're looking at, so it's a face-centered cubic structure. Aluminum, it's a cubic structure with 24 symmetries. That means there's a fundamental zone that if you take this triangle and, for instance, you flip it over this horizontal line, you'll get the same diffraction pattern in this corner. And you apply that 24 times through the different symmetry operators. We can apply, once we know the crystal orientation, we can apply those symmetry operators across and sum and then weight the appropriate replication. So we can see this central region is described multiple times in our single shot diffraction pattern. And what I love is that then we get this final entirely experimental diffraction pattern. So this is the experimental diffraction pattern of the entire stereogram. And hopefully you can imagine why that would be useful for us trying to understand our material systems. So my very last example, hopefully you're still with me, but my last example is just showing you some 3D data as I gathered there's some interest at this workshop in that area. So this is some work that's Shuheng Li's PhD with significant work from Ruth Birch, Warren Poole, and myself to help along the way. So the problem here is that magnesium, it's not very ductile. And so one of the key bits is trying to understand the anisotropy of plastic deformation in magnesium. To do this in Shuheng's work, we've been indenting, or Shuheng has been indenting with a spherical indent, and we're trying to understand the plasticity in the grains. So we do a nano indent. This is our small nano indent inside one grain. And this grain is oriented such that the C-axis is close to the outer plane direction. We then took the sample and we then extracted this particular indent using a sort of TEM lamella type lift out. So we now lift it out. To do this process, we do an electron beam cap. With platinum, we do an ion beam cap to make it thicker. We then effectively undercut from the left and from the right. We leave a lever to hold it in place. We cut around the side. So this is now a freestanding coupon. And then we're going to insert a manipulator needle into the chamber, weld it onto here, cut away the freestanding cut, and then we're left with this token of our material that we can transfer to our TEM lift-out grid. This is very useful because we can now do 3D from a site-specific region inside our polycrystal. So this is now our sample that's located on our TEM type grid. And we're going to basically remove layer by layer each of these. And I said that we have a static configuration for the EBSD. This says that we can do that layer by layer reduction without moving the sample. And that's very important for single crystal analysis in particular, because that enables us to not worry about alignment. That's super helpful for the reconstructions here. So this is just showing you the setup. This is sort of how it's set up before the sample was raised upwards. And then this is the experiment operating in the Oxford Instruments software. So we can see the sample and the angles, etc. So just for the way the 3D setup, we have it sort of aligned in this slightly odd setup, but that's just for the geometry. But we have the indent was running this direction. We're now cutting this section, and we're going to then sort of remove slice by slice into the plane of the page. So I've got the crystal orientation as shown. We've got the band contrast, the misorientation from far field, and we have the IPF data. What we can see in this central section of our three-dimensional volume, we can see that there's a significant plastic deformation that is occurring below our indenter, and we can see these sort of cool wall-like structures, as well as this sort of V-shaped morphology here. And the indent impression has come in and come out. We can see this coming up really nicely in terms of the angle or misorientation, which tells us about the residual plasticity, and that's what we're looking to interpret in a moment. But we did multiple slices, so this is the sort of slideshow through the slices. This is away from the center of the indent. This is progressing into the indent. We have a little precipitate that's popped up and appeared because there are small precipitates in our material. But we can then reconstruct this, and so Ruth worked hard to put this through Dream 3D for this particular software, and then visualized in ParaView. And we now have the indent impression as shown in the band contrast type 3D map. This corner is just due to shadowing. We need to just improve slightly our experimental setup. But you'll see that doesn't stop us doing this analysis where we can look at the residual impression, we can look at the misorientation angle, and we can look through the material if we so wish, and we can look at the orientations. What you can start to see inside the impression is that there's some polarization. There's a rotation gradient inside this field, as well as this between this and the base. And that's all about the plasticity. A simple piece of analysis that Vivian Tong, a long time ago, worked with me on this, is that this rotation gradient is associated with the accommodation of plastic deformation due to constraint. So if you have a material deforming in a constrained volume, if it was unconstrained, the material would deform out of this. This is like if you did plasticity, you do a uniaxial test and you see slip planes, you see a crystal rotation if the grips can't move sideways. It's the difference between pure shear and simple shear. If you rotate this back to fit back in the constraint box, you now see there's a rotation gradient, and that rotation gradient is fundamentally related to the cross product of the slip direction and the slip plane normal. So the rotation axis is out of the plane of the page, and we can interrogate that as the invariant point on an inverse pole figure, a pole figure over here. So we can identify which characteristic slip systems will give rise to which colors in this sort of map. And we see that the interest here is the A basal and C plus A pyramidal of the two slip systems we care about. And so we can see that the sum combination of those slip systems could give us blue. So if we look at our three-dimensional sections in here, so our 3D sections, this is now the cross section through that 3D volume. We can effectively look at the misorientation angle. We can recover the axis from it. Here's the angle. Here's the pole figures for each of those sections. And I said, look for the invariant point. The invariant point is this top point over here. So we can see there's not very much spreading for that point across each of the different sections. And that tells us it's the rotation axis that we care about here. So if you then just extract 2 points sort of either side in this lobe, we can start to see that the rotation axis omega is specifically associated, drop my hexagon on the floor, but it's a rotation effectively about the A1 plus A2 axis in here, which tells us it's related to these two slip systems. And there's some more analysis that's super exciting and ongoing that tells us a little bit more about this deformation structure. But I stress we can only access this through this 3D serial sectioning to build up the full picture of this deformation under the indent. So it just highlights that indentation analysis, we just sort of started in this piece with our 3D data sets, and we're starting to explore new alloy chemistries and fundamental deformation mechanisms. To do this, we need to have new methodologies for the analysis and visualization to get quantitative data from these beautiful three-dimensional micrographs. So with that, I've hopefully persuaded you that EBSD is both an established technique that is immensely powerful. It's kind of scary to think that I think 30 years ago was the emergence of this new technique, And yes, I've shown you some brand new developments that continue to exist in this. It can be used relatively routinely for grain size assessment in a whole range of other bits and pieces, and they're beautiful and very useful, and the software manufacturers have done a lot of work to make that possible. Increasingly, as we get access to the data and there's open source algorithms, etc., we can start to do even more to push the techniques and tell us to solve problems that are useful for society on that. So with that, I thank you for your attention and I welcome questions.
Thank you so much for the incredible talk, Ben. I'll start with a quick introduction. My name is Mike Barsoom. I'm a third-year PhD student in the Dravid Lab and a very active user here at Nuance. I'll start the questions off. So if anyone has any additional questions, please feel free to pop them in the Q&A function. And the first question is about MapSweeper. And the question is, does MapSweeper require saving of patterns?
Unfortunately, yes. So the key thing for MapSweeper, and you'll see this in the next talk, I believe, the whole of the methodology is that it's done offline. It takes a bit longer for lots of good reasons, and we just do a direct image comparison. So we compare one diffraction pattern and we say, what's the best classifier for that particular one based upon the phase and orientation. So I have to say the second piece of hardware that I'm not talking about is all my data. We have some very big data arrays. I think we now probably have like 150 terabytes of EBSD data that's been collected over the years. And I think we're now, with the 3D data sets, probably going to be generating probably 30 to 50 terabytes per year. So it's slightly scary in that problem. So,
I can imagine that starts to become a problem.
yeah.
The next question is, in the Warhol-like segmentation with weighted data, is it just for visualization here, or is the data evaluated across the borders of the segments?
So each of the individual, so the Warhol-like piece here, this is what was being referred to. The visualization here is just that the classifiers, so the blue classifier is viewed as different to the orange classifier, even though it is actually probably the same pattern. It's just we have an independent analysis across each of these frames, and it was simply a RAM issue. To do the PCA, you have to pull the whole data set into your RAM, and I have some big computers, but this was a bit annoying. So, and this creates some small issues. We can imagine a slight algorithm, a sort of seam mending problem, where we could basically overlap and check, should we call these the same thing, and do the data, but that was sort of a nuance that wasn't too important. It does do one subtle thing. So you can see this in this. So I didn't talk through this particular data set, but we've taken the characteristic signal and we describe everything with that label by the chemistry of that particular characteristic diffraction, characteristic energy dispersive X-ray spectroscopy. So what you see is there's this right angle field. That's just because it's filled to the edge. And that's sort of similar to the edge problem I showed you in the EBSD data example there. So again, it could be fixed. It was just a RAM issue, and we were, did we solve the problem sufficiently with the artifacts that we know? So, yeah.
Great, thank you. The next question is also about MapSweeper, and they're curious if MapSweeper is an Oxford software, and in general, what acceptable practices are there for data cleaning, and how much is acceptable in that way?
Mike needs to give me some commission for the next talk, but MapSweeper is an Oxford product that's available as an add-on. I believe it's in the latest version of the Aztec software bundle. There are open source alternatives, so EMSoft, which is built by the Carnegie Mellon Group, and then we also have a tool set in, it's called Astro EBSD, that can be used for some of this. So there are alternatives that do this. None of the data that I have presented has been cleaned up. I should just comment on this. There's been no data cleanup. I don't like it. Occasionally we have to, so there's some specific problems where we've done data cleanup, and that's a software post-processing based upon the spatial observations of orientation data. The huge benefit of doing the pattern matching is you're just looking at the physical signal and saying what's the best classifier. And specifically the physical signal, the MapSweeper is just more sensitive to rubbish patterns. And that's why it improves the information that's presented there. So I'm one of these sort of sad people who gets very excited to see scratches, because it means you've not been messing with your data. So my students in the group are terrified when they present a scratch, but I'm like, actually, I love this, because it tells me this is the real honest truth and we can interrogate this properly. It's not actually important for the story, this particular scratch in that. So different paradigms, it depends on the story. The most important bit, and this is something that Oxford have done a nice job, is that there is now located in your data tree, there's a what did you do to clean up the data? EBSD has got away with a lot of data manipulation where we haven't reported what people have done for the manipulation. If you were in any of the other image processing communities, you would be crucified by journals for what EBSD people have done. So it's finally getting to the point where we now have reproducible algorithms to clean up and we can see the artifacts. Those of us who are experienced may know what the artifacts look like, and so we know where to look, but you can tell a whole host of lies with EBSD data if you do poor cleanup. The important question is it's not to make it look aesthetically pretty. That's what I guess the most important thing I should share here. It's what is useful for the problem that you're interested in. So here, I don't care there's a scratch because the problem I want is I want to find a yellow grain. I want to find that needle in a haystack of that single grain across this region. That's all I care about. I can put this, if I need to, in the paper or the supplementary. There are worse EBSD maps in the literature, but I can put this in the supplementary if I need to report this fully. But it's, did this help me in that problem for that?
Great, thank you. Here's a question from somebody who was having some problems with sample charging despite using fast scanning when they were using TKD. Do you have any suggestions for how they can solve this problem?
Yeah, so charging typically because the electron dose isn't being sent to ground. So the most important thing will be how have you welded the sample or stuck the sample together, and how is the sample holder set up? We have some issues. We don't quite like our holders, and we're redesigning some new ones to reduce charging. So the other piece is sample cleanliness. So if you get, these are all thin foils, and the SEM doesn't really like small samples. The whole thing's set up to have a bigger thermal mass and a bigger surface area. And so those sort of issues. So keeping your samples nice and clean, checking there's a good ground. And the secret bit of the ground is it's not necessarily the foil being held by the grippers. It's perhaps the grippers and other bits and pieces. So see whether you can ultrasonically clean all your holders before they go in the SEM. And the last bit for drift type issues is thermal mass is important. So preferably keep the sample holders, etc., in the same room, in the same HVAC system, so you have a temperature, and don't be too much of a rush. So you need a little bit of time for things to settle when you're in the microscope for that drift issues. The last bit is that all the data I showed you is on the good days. So we've had many bad days, and so those ones are where we just don't show the data and we just have to give up. So the yield on TKD, a colleague, my brain's gone blank who it is now, Pat Trimby from now at Oxford Instruments, he used to run the Sydney labs, and he said everybody wants to do TKD because it's exciting. I would always say to people, can you do it any other way? If you can do it any other way, that's great. TKD is very useful, but it may not be the best way to do it. Certainly if you've got a well set up lab for that.
Great, thank you. Building on the sort of sample prep kind of question, sort of selfishly now, I'm going to ask one of my own questions. I'm wondering if you have any recommendations for taking EBSD of powders, especially that are non-conductive, if you've experienced that before in your experience.
I have done a little bit, not hugely. Typically you would embed. So the first thing to do is to get the particle so it doesn't move. So you want to embed it. Think about the heat treatment that happens in the embedding process and the forces. Sometimes that's fine for powders, but it depends on your material. So do you get transformation, etc. So once you've embedded it, you then want to get it nice and flat. And so sometimes, for instance, with if you want to choose the embedding resin to have a similar hardness to your particles, so that effectively you don't get surface roughness towards the edges because they've got shadowing and other artifacts in that. If you can't do that, you need to think about cross-sectioning. And so you can cross-section the material. We have a broad iron beam polisher that's very, very useful for cross-sectioning. There you just need to worry a little bit about the conduction of what you're cutting through and where the sputter yield's going to go, and not gunking the instrument up for other people. But cross-sectioning can be very useful for dissimilar phases. Then the last bit is for charging on these objects. There's sort of three methods to reduce charging. So charging is related to the total electron dose and the energy of the electrons. So if you can reduce the voltage and or probe current, that could be helpful to get you to be sufficient. So if you can run the system faster, you have a less total dose per unit time per diffraction pattern. You may compromise the diffraction patterns, but they may be more correct for the region that you want. The next piece, so you could reduce the voltage. Just be very careful. You don't want to reduce the voltage too much because there's an efficiency of the scintillator. Scintillators typically have good sensitivities above, say, 10 to 12 kV, unless you spent a bit more money. So think about that if you're dropping the voltage. Also, the Hart-based algorithms can mess up at lower voltages because the bands are wider due to the n lambda equals 2d sine theta. The last method, or sorry, once you've done those bits, you could also coat the surface. So you can put a thin, say, carbon coating across the surface, and that can dissipate the charge. And then in those cases, you actually increase the voltage to get through the coated layer. So you're going to go up to 30 kV, and then you might nudge it down depending on how you play, but you want to have a controlled thickness of that sample. The last and final method, which is used often by the geological community, is to insert an imaging gas into the chamber. So to use a variable pressure and introduce perhaps a very small amount of water vapor or other gases that can effectively dissipate the charge through the formation of the charge cloud. So you'll get a slight reduction in the diffraction patterns because they're going through the imaging gas itself, but the gas itself will deal quite nicely with the charge cloud in there. And some microscopes are equipped with charge cancelling guns, so you can flood a certain fit to have those. They're often not well set up geometrically for EBSD stuff. So a few different suggestions on that.
Wow. Yeah, thank you for the very complete answer. I think we have time for maybe one more question. And so this question is about severely cold deformed materials and how you can improve indexing on materials like that. For example, they suggest aluminum alloys in terms of time accuracy and accuracy of data.
So there's a nice example in the literature from the Carnegie Mellon Group who have used pattern matching to improve the spatial resolution. Specifically there, the pattern matching method can improve the resolution of poor quality patterns. So fundamentally, the key thing is actually not that it's severely deformed, it's that there's strong strain gradients within the interaction volume. So the fact it's severely deformed, if you have a ceramic system that's severely deformed, it's got the dislocations tend to lock themselves quite close, it will crack, etc. But the key thing here is that it's soft and smears. So you want to think about that, what's happening inside the interaction volume. So decrease the interaction volume size. That can be reduce the voltage, play with the probe size, etc. in that. But then the next thing is once you've got good focus as well, is then to think, okay, how do I improve the diffraction pattern analysis to deal with effectively blurred patterns? And so that's where things like the pattern matching can get you out of that point in there.
Great. Thank you so much. Thank you again to Ben Britton for his nice talk and very thorough answers. We're going to take a short break now, maybe 5 minutes or so. So we'll maybe return back to Zoom at 10:40.
Moving on, it's my pleasure to introduce Mike Hjelmstad. Mike is an applications specialist for Oxford Instruments Nano-Analysis and has been with Oxford for about a decade. He is no stranger to the Midwest and studied at the University of Michigan. I believe you're from the Midwest, and has been helping us here at the Nuance Center for several years. I always reach out to Mike whenever we have unique EBSD, WDS, or EDS problems. Mike has also trained me personally on a lot of these things. So I'm excited to welcome Mike back to Northwestern to give a talk on what's new at Oxford Instruments, including specifically the MapSweeper software, which a bunch of you were asking about in the last talk. So without further ado, I will turn it over to Mike.
Thanks, Tirza. I hope everybody can hear me all right. Let me start sharing my screen for the presentation here. Hopefully that looks good. Yeah, thanks again, Tirza, for the introduction. Yeah, I'm a Midwesterner. I was from Minnesota, Michigan originally, but yeah, now in California. I'd actually like to start and give Ben a thanks too. He's right. I probably owe him a little bit of a residual for the pattern matching questions that came up this morning. But actually, before I go on, I mean, I really want to echo what he stated about, cleaning data, so to speak, is, you've got to be really, really careful. And there have been some liberties taken in the EBSD world that, like you said, really would get you crucified in other disciplines. So, I'm kind of leaning into, pattern matching here, but it's a tool. It's not a solution for, poor prep, poor sample setup and things like that. So, as the title says, I'm going to talk about, overcoming the real indexing challenges and using pattern matching to do it. And I have to really thank the two collaborators on this. First off, Imel Winkelman, who did really develop a lot of the technique that we're going to talk about in this presentation, and Pat, who Ben also brought up, He's the product manager at Oxford that's done a lot of work in getting this into the software with Aztec Crystal. So I'd like to start with something practical here. This is Greenland. This is 2022. This is a couple colleagues of mine who were doing, well, a couple colleagues of everybody on the talk doing geological research. And you're 100 kilometers from the nearest settlement. I mean, there's a part of me that looks at that and goes, looks really interesting. It looks kind of uniquely beautiful in a way. But the problem that came up for them is this. That's why their tent's there. And I swear to God, that's not a dead body under that tent. It scared me the first time I saw the picture to some extent. But effectively, you've had a tent pole that just absolutely snapped dead in half. And if you look at the part, that's what you're dealing with right there. And given the researchers that were on this trip, they have EBSD. They go, let's dig in and find out what really caused the problem here. So started with a little bit of sectioning, a little bit of sample prep, and kind of locating, what was potentially a crack initiation site, and really getting to the bottom of, can we figure out what really caused this problem here? So that's kind of the micrograph at low mag. This is kind of where we went in and did the EBSD analysis. And I think this is probably fairly typical for some researchers on the talk today. You get a pattern quality map where you got a wide distribution here. There's certainly cases, and sorry, I kind of jumped ahead a little bit, but this is an aluminum sample. When you look at areas with good pattern qualities, you see what you'd call maybe a little bit of a fuzzy pattern to be expected near high areas of deformation, but that's something that can be indexed easily. There's areas as we get a little bit closer to kind of the high deformation area where pattern starts to go off a little bit, but we can still index it. And then there's areas where we just are going to struggle for a legitimate pattern. And when we try to index that, it's just a complete failure. And so thus you're left with an orientation map that looks something like this. And is it really telling you the whole story there? It's difficult to glean a lot of information from that. One of the things that was noticed in the analysis was there were inclusions in the sample. There was a magnesium zinc inclusion. There was a copper iron inclusion that was kind of noted in this. So if we look at the phase map, we kind of see these inclusions kind of peppered about, but it actually represents another problem in this sample. Is we can kind of look near the magnesium zinc inclusion here, and get a pattern that looks pretty good. But the three phases that we're indexing against, we can find a way to index as the manganese zinc. We can find a way to index it as the iron copper base inclusion. So we're kind of left with the, I'm not sure what it is. And when we look at it in finer detail, we just start to kind of get this mess of a phase map. And so that's kind of a practical problem that leads us into, what can we do? What's the solution that we're kind of offering here? So I'm introducing, Map Sweeper, and this is something that exists within Aztec Crystal. And the whole motive of this was, when we do regular Huff transform indexing, and I'll kind of come back to this, but when we do it, it's kind of a binary situation. You either solve it or you don't. You can obviously measure degrees of how successfully you solved it, how confident you might be in it, but it's kind of a yes or no question. And what pattern matching is simply just image correlation. It starts with pattern simulation, and I'll talk about that a little bit, but it's straight up using the measured data point that you have on the left there with the simulated pattern, and just looking at the differences between them. And so that's kind of the crux of the talk here at the beginning, and kind of how we do this. So what's going on in pattern matching, and really the development of this in the last couple of years has been really building better simulations, and kind of point back to Imo's work back in 2007, where he was kind of introducing dynamical EBSD simulations. And this is actually a pattern, a collected pattern that you see on the right. And as I kind of change here, that is the actual simulated pattern. And it's kind of striking how accurate they can be now. And, ultimately, this is something that was really, kind of pitched a while back. Stuart Wright was the first one that really put a publication out that kind of said, why aren't we comparing this to kind of a simulated Kikuchi set and really determine an orientation from there? Ultimately, what caused that to kind of go away was when Huff transform and Huff indexing was kind of introduced and kind of improved, the speed of Huff indexing is dramatic compared to what you would do with pattern matching. Even as the computers are improving, Huff transform has always kind of overtaken it and become kind of the method of choice, I guess you'd say. Recently, the pattern matching has become kind of the emerging, exciting technique. It's more because, technology is kind of catching up. The simulations are better, the computers are better, so you can actually do this in a manageable time format. So kind of going into the history of this here. One of the first pattern matching techniques that was introduced, and really most people will recognize Mark de Graaf's name on this, but the dictionary-based indexing. And the publication of those probably from M&M in 2015, but they were basically building a library of all the potential patterns that you could get. Like it says, a dictionary of, thousands and thousands of templates, even a million in this case. You can imagine when you get to kind of lower symmetry patterns, you're going to have to build a pretty significant library here. So that technique, was kind of, it was introduced. It was an interesting idea, but ultimately the practicality of it was poor. It didn't necessarily. It was going to be something that would take quite a bit of time to set up and then even run, and that was even on heavy duty computing. Another technique that's been introduced, and this is used by other folks out there in the industry, is spherical harmonic indexing. The best way I can kind of explain this is it takes the patterns, it takes a simulated, I got this wrong. It takes the patterns that you're actually collecting and kind of transforms them into a spherical model and then matches that to a spherical pattern simulation. So the theory here is that it could be quite a bit faster, but it's complicated enough that I probably explained it quite poorly here just now. But it's not something that can take account certain geometrical differences with setup between microscopes and stuff. And so the last one on my list is the hybrid approach, and this is the one that Emil Winkelmann has kind of recently reintroduced, at least at M&M in 2020. But it was to build on the Huff indexing that we already have. So it's something that he's called hybrid pattern matching. But rather than build these big libraries of patterns or simulations, I should say, we're going to take the Huff indexing as a starting point. We're going to basically look at patterns that are very, very near that orientation and see if we can effectively fine tune or even kind of quote unquote repair a zero solution in a sense. So I'll kind of go into this a little bit more. I forgot to take that slide out. Apologies. So this is MapSweeper in Aztec. It's the hybrid pattern matching method. We'll go into one of the other sweeps that's part of the software. But we're hoping to kind of solve problems for a number of different problems that are going to arise during the indexing steps. Mainly trying to index poor quality EBSPs. Hopefully the reason you have poor quality EBSPs is sample related. And like I said, if you're not doing the sample prep good enough, that's not the reason to use MapSweeper. We're talking about highly deformed patterns, and other kind of tricky things would be similarity between crystal structures, like we kind of showed in the tent pole problem here. We even get into pseudosymmetry and crystal polarity, and I'll kind of talk about these in examples, but you want to dig into a lot of examples. I like to point people towards the EBSD.com website. but there's a quick process flow there. MapSweeper itself is part of Aztec Crystal. And so I think some of you are familiar with Aztec Crystal. It's the post-processing tool that Oxford Instruments does that kind of works with Aztec on the acquisition side. It's something that we redeveloped and introduced back in about 2019 was the first iteration. And by about 2020, we were able to put to bed an old software, Channel 5, which I'm sure if people use it, they might groan a little bit. It was good for quite some time, but it kind of worn out its welcome by the time we introduced Crystal. But this is kind of an example of the navigator here. You can kind of see the highlights in some of the cases. It stems from the Crystal software. Again, we're gonna kind of set up different sweeps. We're gonna kind of execute at the very end of this. And kind of leading from that interface, you know, the first thing that we need to talk about is the pattern simulation. And it kind of leads me into the other sweeps because depending on what sweeps we're going to do in MapSweeper, you're going to start here at the pattern simulation. And I kind of talked about the dynamical simulation. The other model that exists is a kinematical simulation. And really, you can kind of see some of the differences along the bottom right there. It's kind of showing us the experimental pattern and what we would simulate in kind of the 3 different types of pattern simulations that we can produce in MapSweeper. Obviously, we'd like to kind of go the full dynamical. You can see it takes into account kind of the multiple diffraction events and really builds, you know, ultimately a better picture. I mean, it's easy on your eye to even look at it and go, that looks more representative of the patterns that I see when I run the system. The only difficulty is dynamical simulations are a little bit more difficult to produce. They take a little bit more time on the computer. If you do something that's really high symmetry, cubic materials, you can make these dynamical simulations in 2-3 minutes. It's very, very quick. You start to go to low symmetry, you know, triclinic type cells, can take hours, admittedly, and this becomes, you know, computer intensive so that your GPU power can actually be very, very effective in kind of bridging the gap that you're going to have with dynamical simulations. So starting with this simulation, MapSweeper is really going into, you know, what are we going to do next? There's 3 sweep modes that we've introduced with the software package. And I'm going to kind of break this down a little bit more. So I'm going to kind of go through this slide pretty quick, but there's an indexing sweep where we're really looking at patterns that are very, very poor in trying to get something out of it. You know, where Huff indexing is going to be really, really, it's going to be impossible, basically. There's ways to maybe solve, but, you know, get very, very low confidence where, you know, pattern matching is going to be, you know, something a little bit more quantifiable, something that might be a little bit better. It's going to use something called dynamic template matching that I'll talk about in a second. The other 2 are the 2 that I see some people using quite, you know, more often. It's something that is really practical for a lot of samples. And the first one's a refinement sweep that's going to use the Huff indexing as a starting point and effectively try to see if it can get a better match to the pattern than what was originally solved via Huff indexing. This is something that'll help us solve pseudosymmetries, similar crystal data, and I'll get into that shortly. And the last one is the repair sweep. And I know we kind of got on the topic a little bit during Ben's talk, but you know, traditional data cleaning in EBSD is really kind of a statistical model and looking at nearest neighbors and kind of determining how many of them have to match before you can kind of fill in the blanks, so to speak. And there's ways to take wild liberties and basically create false data. With the repair sweep, the whole thought here is there's something in the pattern that might be usable. And let's start there rather than just starting to look at nearest neighbors. And with repair sweep, we often look at nearest neighbors just to get an idea of what the orientation might be and seeing if it can actually pattern match to a high degree what was collected. So I need to talk about the indexing sweep. That's kind of the brute force model here. So We kind of internally called it dictionary-less dictionary indexing. I kind of mentioned earlier that with dictionary indexing, we create thousands and thousands of patterns and do the matching off that. Here, we still have the template in its kind of spherical form, and we're generating the individual patterns on the fly. So this would be something where you would do your regular EBSD, you would collect your map. This is an example of a really good map where maybe you don't actually need the dynamic template matching, but you have your simulation master there. That's presented in 2D, but kind of think of it as a 3D simulation. And we're going to look at, you know, a pattern that we've collected. When we're doing DTM, it's probably going to be a poor pattern to begin with, but we're creating, you know, segments from the original pattern simulation and seeing does this match better. And you can kind of tell there's some very, very wild different orientations that we're going to go through here. I shouldn't say it quite like that, but we're going to go through not very subtle changes. These are going to be, you know, a couple degrees of orientation change for each one we develop. And then we're going to kind of fine tune and hone in on the best match and, you know, come up with a solution. And that's going to dictate our phase and orientation data from that. So you can imagine that if you're generating this many patterns, it could take some time to actually, you know, focus in on a solution here. The good news is it actually will come up with a solution every time. The bad news is it will come up with a solution every single time. And so, you know, I'll give you an example first, and then we'll go through kind of the correlation factor that really helps us determine if we did a good job or not. So the perfect application example for this is the highly deformed samples, where the patterns just go fuzzy and eventually you're almost losing crystallinity of the material to the point where you don't get a good diffraction pattern at all. You know, this is examples where you might get 50% indexing going in. And a good example, like I say, cold rolled metals, you know, we're looking at high strain rate geological materials, you know, meteor impacts, kind of an interesting one to me, or something that's been, you know, surface treated in a really highly mechanical way, a shock peen material or something like that. And one of the examples I can show is an impact diamond, and this was research that was done at University of Leeds with Sandra Piazzola's group. This is an example of the patterns that were obtained off this impact diamond. And this was a TKD sample to begin with. So quite a bit of difficulty in solving that. You're not going to go anywhere with Huff indexing for the most part. You can see some structure there. It should remind you of the tent pole that we just saw at the very beginning. If we do just Huff indexing, this was 51% indexing. And if we put it through dynamic template matching and then a quick reanalysis with the refinement sweep. So it was kind of two sweeps in one, but we were able to build this data set up to 98%. You can kind of see that the data really does agree well, but I kind of appreciate Ben's opinion, you know, where he was showing scratches in that map where you kind of go, I'd rather see something that shows experimental error rather than just magically, you know, painting everything there. So I admit that image on the right scares me a little bit. And, you know, it could provide some good data. This is one of the cases where what are your options? You know, and it's going to be very difficult to go back and do the prep better. I mean, it's done via TKD. It's probably as good as it's going to get. So again, it's a tool, but, you know, kind of go back to this situation of, you know, it indexes anything in this dynamic template matching. And, you know, the joke that we kind of had in Oxford was, can you index an elephant? And so this is just a grayscale image. And if you look at it, if you run it through a dynamic template matching, I can find a pattern that fits. And the key detail here is there's an R value, cross correlation factor that's printed at the top of that image, 0.112. That would be what we'd consider a poor match, but it's a match. So again, I kind of want to get into this metric. Here's an example of an actual pattern. And this is one I think I used earlier in the presentation, but we've come up with a solution here. And the correlation factor is about 0.14, kind of, you know, straighten teeth a little bit and go, that's not good enough. And in fact, it's almost as good as just putting an elephant in the image there. But I do want to talk about, measuring the image similarity, because this is obviously critical to anybody doing map sweeper. So what we're doing is we're putting the patterns and the simulations on kind of a similar grayscale value. We're trying to come up with the average grayscale. We're calling that 0, and we're effectively measuring how many standard deviations away from that average any one pixel is. So we kind of get things on a normalized scale, and then it's just straight up, matchup of the two patterns there. And what we're showing in MapSweeper in blue is an indication of a case where the actual experimental pattern is a little bit brighter. In the case of red, the simulated pattern's a little bit brighter. And if you care to kind of dig into the research a little bit more on cross correlation factors, there's some citations there to go with. But we're effectively building an R value that's somewhere between 0 and 1. Kind of the numbers that we're looking at right now, and this is still up for debate, but something around 0.2 and above might be acceptable. Below about that, it's kind of being questionable. In this case, we're at 0.8. You can see we already had a good pattern to begin with, so it's not terribly staggering that we matched it at a very, very high cross correlation factor. But I do want to talk about why we use a normalized cross correlation and not a normalized dot product. This is the example of the elephant again. But what we've kind of done in varying degrees over here, going left to right across, is we've changed the brightness, or we've changed some of the contrast a little bit. Sometimes it's been done to just the image, sometimes it's been done to the simulation. But what was kind of staggering is if you use a normalized dot product, you can start with a really, really high correlation factor, but just changing the brightness, you can kind of see in the third frame here, just changing and raising the brightness of both images gives you a better correlation factor. Since we're normalizing everything first and using the cross correlation, we are consistent throughout using the image and changing contrast and brightness of the various images here or simulations. When it gets to something that's completely noisy, the dot product still gives you a number that you'd almost be convinced that was a good match, and there's no detail there. Luckily, we see it when we use a cross correlation, it falls off completely. And so I think we have a robust metric there that we can use to say if a solution's done correctly. And that's something that you could turn around and plot in Crystal and say, here's my belief in this, here's where every data point kind of sits. It's not kind of being hidden behind the scenes or anything like that. So kind of sets me up to go into the other two sweeps. This would be refinement and repair sweeps. I'm going to focus more on the refinement, but I think of these as being done in tandem. And this is using the hybrid pattern matching. And the whole motive behind this is, well, what if the original data is not so bad? Here's that tentpole example again, where there's a good portion of this that's pretty good. This is an example of a deformed titanium alloy. You look at that, and when I originally saw it, I thought, we're getting like 90% hit rate. It turns out it was closer to about 70, 75. But there's a great starting point there. Here's an example with kind of mixed phase. You kind of see this now and then when you get similar crystal structures, where you get that sprinkling of the different phases. And another example would be this is a geological case, but again, kind of higher strain and kind of trying to analyze multiple phases there and kind of get the numbers, or get the phase ID correct. So what hybrid pattern matching does is basically says, why throw away the original data that you're going to do? You're going to collect everything the same way you did before. You're going to do your Huff indexing, so you have this orientation map that you collected. You have your simulation, just like dynamic template matching. You look at a given point. In this case, you have a starting point. This is a solved solution where you kind of go, I think Huff indexing has told me quite a bit. And I'm using a great example in the experimental data, but you can imagine kind of a, I'd say so-so, but you have to kind of do EBSD to see what tends to solve, what's poor, but what we're going to do is take the initial data that we did with Huff transform and make subtle changes. So notice the orientation difference here. It almost looks the same. There's just very, very slight differentiation there. And if you can see this on your screen, it's actually kind of doing this refinement. It's kind of doing a regression to kind of see which pattern fits the best and get the maximum R value. And you can see this little shift. It almost looks like there's, it's kind of moving in and out of the page, not just shifting, but we're trying to kind of fine tune the solution and come up with exactly the right orientation and phase for this one. So the bonus here is it's fast. We're not going away from the Huff information dramatically. So we're not creating thousands and thousands of patterns or anything crazy like that. It maybe is 100 to 200, but this is something that, I can usually do it about 1,000 patterns per second. I've seen some of the nice workstations that just obliterate and go twice as fast, 3 times as fast. But it's realistic to do in a couple minutes, not hours and hours. And really, I think where we've come to is you may only need the hybrid pattern matching to get the job done. Going full dynamic template matching might be a bit excessive. So let's talk about some examples. And this is just an extension of what we talked about with dynamic template matching. There's cases where you get deformed materials and you get, poor patterns, but they're not to the point where you really need to go back to the drawing board or you need to find the dynamic template matching. I'm kind of thinking of, maps that index on the order of 60 to 80% kind of neighborhood here. Things like this, again, deformed metals and alloys. This is really kind of goes back to some of the samples from DTM, but maybe the amount of deformation just isn't quite as significant, and you kind of have a starting point. And the good example was that deformed titanium that I just showed previously, and I think I said 75%. There it is, 79% was what we got. But you see the example EBSPs on the right. You have some pretty good data there. Some people might roll their eyes and say, pretty good. I don't know if that's good enough, but there's more than 2 or 3 bands that you're seeing there. You have kind of a starting point. It may index poorly in Huff. It may not index in Huff, and that's, again, maybe something you need to do with DTM. But this is an example at 12 kV. The initial run was quite a long run. If we put this through a refinement sweep and a repair sweep, we get kind of a nice data set there. We kind of fill in a little bit of the blanks, but we're filling it in with the actual captured data there. It's not just kind of voila, paintbrush fill kind of thing. So that's an example of one of the goals. We're removing a lot of the errors, but we're also improving angular precision as we do something like this. We're kind of dialing in even all the points that we actually index properly the first time around. We're kind of dialing in exactly what that orientation is. So no duplication of data. Another example is kind of the high precision analysis of something that has a lot of dislocation. So maybe something that has decent patterns, but when you put this through Huff indexing, you're not revealing the subtle differences between this. And this is something we focused a lot at Oxford on trying to improve. We've kind of brought out the refined accuracy band detection and kind of done this 2-step, but that's something that takes a lot longer to do the acquisition. With refined accuracy, we can kind of get angular precision down to about 0.05 degrees at best. You're talking about something that you're not going to do faster than about 200 patterns per second in the initial acquisition. If you put this through Map Sweeper, we can actually improve the orientation precision. And what we kind of are seeing is something on the order of 0.01 is really possible with this. So some of the examples that we've done, talk about gallium nitride, thin films, talk about SIG solar cells, and I'm going to come back to that one later. But dislocation structures and deformed rocks and minerals here. So one of the first ones I kind of bring up here is, this example of geological samples being lower symmetry, being a little tougher to index right from the very beginning, and kind of using hybrid pattern matching to kind of clean up the data set. And this is a Gabbro sample. There's multiple phases in here, and we've used the refine sweep to kind of make sure that we got all the phases accurate. But what people really wanted to study in this was the anorthite grains, the grains in blue there, and really looking at deformation in the anorthite grains. And this is just this is actually the weighted Burgers vector map. So this is a dislocation analysis. There's similarities to kernel average misorientation, without diving way into this, there's similarities to it there. But what we really notice is the grains are a little bit noisy. We're not really seeing the fine detail that we're hoping to. And to kind of focus in on this, here's one of the grain boundaries in that sample. And you kind of see the anorthite grains on the left, and you kind of see this just real kind of noisy blue kernel average misorientation map. You're just not seeing subtlety. You wouldn't necessarily look at that and go, all right, I can see all the subgrains, I can see all the deformation going on. I see a few dislocations, that's about it. On the right is when we go through the orientation refinement, and we actually really do see the subtle changes. We kind of find out that we can improve the angular precision, thus reveal a lot more detail in the substructure there. The dislocations in the gallium nitride is another great example. So this is threading dislocations that occur when you grow thin films, and it's lattice mismatch between the substrate. And as you grow thicker and thicker films, the dislocations start to increase. It's something that you want to understand if you're going to improve the efficiency of the device. And there's a lot of work that's been done already, especially on gallium nitride threading dislocations, but using ECI, electron channeling contrast imaging, or cathodoluminescence to do the analysis and reveal them. When you do this with conventional EBSD, those dark spots that you kind of see get muddled. You really don't necessarily see the orientation changes well enough. But if you can go through Map Sweeper, and that's what we've done here. We've gone through Map Sweeper, and then we've done the dislocation analysis in Crystal to really reveal all the tiny dislocations there. And the dislocation analysis software actually allows us to really reveal whether or not these Burgers vectors are essentially into the plane of the image or out of the plane of the image, and which actual crystallographic direction they align with. So without that, you're kind of lost in the dislocation analysis without getting the better angular precision. Sorry to say. Like I said, we're seeing detail below 0.01 on some of the refinement sweeps here. And then one of the ones that I use quite a bit is enhanced phase separation. You can envision that when you use EBSD, it's a crystallographic process. It does not care about chemistry. And giving EBSD copper and nickel, for example, you can obviously index them very much equivalent. I actually forget the alloys that Ben showed us in the previous example, but you had different elements on different lattice positions, but effectively the same crystal geometry, and that's going to struggle. And we've had ways to combat this. We've done phase grouping. We've kind of created this true phase algorithm where we're using EDS to help, but ultimately that can be difficult. There's kind of limitations, that's the right word, limitations on the EDS because of your interaction volume compared to the EBSD interaction volume. So, a good example of this is, the oxide scales that I'm going to get to in a second. Intermetallics is probably one that I see the most. People working on these nickel alloys and looking at precipitates and things like that. So here's the example on the oxide scales. This is something that's, basically a ferritic steel, but it's got this scaling kind of on the left side of the image there where we have, different stoichiometric forms of the iron oxide. So some of them present as cubic, some of them present as trigonal, like the Fe2O3. But basically when you index that, you get a little bit of a mixed bag where the patterns are really, really good, it might have enough information on the Huff indexing to distinguish it. It certainly can solve these patterns because the patterns are usually pretty good. It just struggles with the phase discrimination. And if we go back and we actually look at this from the pattern simulations, we can really improve the phase discrimination, really present a better picture of what's going on in the sample. And this one, this is a pretty significant data set. This is something that took 80 minutes. And I've kind of been talking about minutes and seconds earlier, but we're not talking about multiple hours. We're not talking about days of reanalysis here. Again, it's something that's actually practical. Perhaps the last kind of example in the hybrid pattern matching is really the subtle pattern changes. And I kind of had that earlier, but what I mean here is things like pseudosymmetry and polarity in this. And this is something where Huff-based indexing is almost never going to get some of the polarity changes right. The patterns, when you see the differences, it's on the fine details. It's on the 15th and 16th brightest band. It's not on the major diffraction bands that you're going to get. And again, we're trying to solve this pretty quickly. We're trying to resolve the pseudosymmetry rather than just flipping the data like we kind of have in the past. Again, the cleanup is a little bit too liberal in a sense in the crystal software to begin with. So this is a SIG solar cell that's copper, indium, gallium selenide. You look at SEM imaging. This is just a backscatter image that you're seeing, and you can clearly see there's some kind of substructure in that film. Some kind of changes in domain structure. And unfortunately, when you index this in EBSD, this is the weighted Burgers vector map, again, similar to kernel average misorientation, but you would expect to see something that kind of mirrors what you're looking at in that image. And unfortunately, you don't. And so we're going to use MapSweeper to reanalyze the data. And really, if I kind of show the example here, this is just a quick animation that's kind of flipping back and forth between the various, how do I want to say it? You have a slight domain shift here in this case between the dark and kind of brighter phases in the BSE. And it's enough that when you look at that pattern simulation that's changing, there's the Huff indexing is not going to account for that difference. But when we do pattern matching, we can really look at it and see differences here. We can kind of go through various rotation transformations there and see that there is kind of one orientation that works better. And when we actually plug it through this data set, it reveals the domain structure there. We see the localized misorientation there. We see the Burger vector kind of magnitude increase. And we can even characterize that, there's a dominant 110 Burgers vector associated with this. If we had just done regular indexing, it would have kind of fallen over. Maybe the one thing that can help folks, I kind of like to show this video here. Hopefully it starts. This will give you an idea of what it looks like in the software. So this is an example of high carbon steel. If you look at the grains in yellow, those are our cement-type grains. I know there's notations here, but I'll just try and narrate over it. But effectively, if you look at that image to begin with, we see a lot of red, blue, and yellow kind of near these cement-type nodules. And we've loaded in the simulations already. We didn't go through actually generating the simulations, but we've done a calibration. So for this actual map data set, we kind of really determine the exact projection parameters. We kind of really fine tune where the pattern center is, what the insertion distance of the camera is, kind of effectively identify what distortion we're going to get. And then we start to go through and pick which sweeps we're going to do. And in this example, we're turning on the refinement sweep and we're turning on the repair sweep to see if we can build up the zero solutions. And we're allowing the repair sweep to run twice just to see if we can clean up some zero solutions that might be, how do I want to say it, improved by solving data around it. And when this runs, it runs very, very quickly. If you were paying close attention, when we got to the refinement step, one of the things that we did was actually bin the pattern simulation, the patterns that we already acquired. So we actually went to a little bit lower resolution, but the pattern simulation, the matching holds up. We actually get really good correlation to the point where you feel confident in kind of changing the experimental data here. And you can see it going through the first repair sweep. When we come back with the second repair sweep, it's even a little quicker because there's fewer zero solutions. And we've really taken this from a data set that was, a little bit muddled to something that's really telling a lot better story. And rather than just overwriting the original data, which I think would be almost a crime in itself, we're going to save this as a new data set. And now you've seen that we've gone from about 78% indexing to 99%. And really, when you look at that, the phase discrimination is really quite good and something that you can kind of move forward from. Oh, sorry, didn't mean to do that. Let me go through there. Okay. Maybe the last thing to talk about and start moving on. What about TKD? And you kind of saw the impact diamond. That was a TKD sample, but the pattern distortion, the geometries are quite a bit different. I think I've gotten questions with does it work for that as well? And the answer is yes. And when you look at TKD, again, I've had Pat Trimby say the exact same thing to me that Ben reiterated is, are you sure you got to do TKD? Perhaps there's a better way to do it, but at the same time, sometimes there is no better way to do it. And usually it's a difficult sample, or usually it's a very, very fine resolution sample that you're looking at. But again, this is the case where, what if you just don't get good enough patterns? It's just something that's difficult to work with, something that's very nanostructured, where it's tough to build a lamella thickness to an effective thickness. Sorry, what's the word I'm looking for? Trying to build the lamella thickness properly to kind of capture single grains through the lamella rather than potentially multiple grains. Again, highly deformed materials would qualify, but nanoparticles work well here. And that's the first example I have is copper nanoparticles by TKD. And really what you had is, in this example, there was a little bit of clustering. It was hard to kind of segregate the particles out very, very well. This is something that's on a TEM, a holy carbon grid, and we just did TKD on it. The initial results, it's hard to write home about that one, 12%, and when you look at some of the patterns, they weren't good enough to solve via the Huff indexing. We've reprocessed this data set a couple ways, and it's kind of interesting to see the results. We did this one with the refinement sweep followed by a repair sweep and brought it up to about 47%. Now that's global across that map, and you can obviously see we got a lot of open space that's not actually particles, but we kind of reached about 47%, and you're telling a lot better story on the particles there. If we do dynamic template matching followed by the refinement sweep, and it's kind of, how do I want to say it? It's a little odd to do DTM followed by refinement because there is a little bit of refinement built into the DTM. But this can improve it a little bit more. Got to about 54% with that, but it was something, when you look at the two side by side, you kind of realize that you didn't create any data differently between the two setups that we had there. This is an example with a highly deformed duplex steel. This was high pressure torsion tested, but what you're looking at here on the left is the original Huff indexing. If you look at your BCC that's in red, decent job. It's not something you have to go back on, but the FCC, very, very poor analysis. And what was done, if I'm not mistaken, in this case, it actually used DTM on the FCC grains, or the zero solutions plus the FCC grains. But then we just did a refinement on the actual BCC solved grains. And on the right, you can see you got a grain structure that's well resolved here. We can come back and we can actually characterize the FCC grains and say there's an average of roughly 55 nanometer grain size there. But you're building an actual grain list of about 1,600 patterns, or sorry, not patterns, grains, to do the analysis. And then this one's kind of a nice one to show, you know, really, really fine resolution here. So this again, this is the, I actually forget the material on this. So this is a nickel alloy. And if you look at the original Huff indexing, it's really what you'd say was a decent map. I think people that have done TKD would look at the map on the left and go, that's quite a good job. If we do some refinement sweep, we can actually build up the data with the repair sweep. If we look at the fine detail, you can see kind of the notes here. The refinement sweep followed by repair on the right, 97%. And when we kind of go in and look at some of the grain structure, there's twin boundaries that we discovered in this map set that are literally like one step across. It's 2 nanometers wide. We're looking at grains that are sub 10 nanometer here. So it's data that really was kind of missing in the original Huff indexing, but you had to be pretty close to kind of make this last final step here. And maybe one other one just to kind of show all the sweeps working together. This is a deformed 304 sample. If I look at some of my regions where I have good pattern quality, you know, this is easy pattern matching. You can see the correlation factor of 0.79. There's a part of me that would almost go, do you need to do even hybrid matching on these? But this is an example where the patterns are so good, you certainly wouldn't have to do DTM. The Huff indexing is going to be good enough to begin with. You know, start there. Don't go crazy on the indexing sweep. If you want to use refinement sweep, again, why are you doing it is the first question. You know, if it's to resolve some fine details, okay, great. But this one's gonna solve pretty well. So DTM is certainly excessive in that case. Same sample though, has regions right here, and it's different phases as well, but it has regions here where, you know, we really did struggle to get patterns. And this is where, you know, the deformation is higher than kind of the surrounding region. And DTM really allowed us to actually come up with a solution for this. I would argue maybe that the one on the bottom is perhaps a too low of a cross correlation factor. And that's something that you set in the software. But, you know, this is a case where you can kind of use both sweeps, really all 3 sweeps, I should say, to kind of build up a better data set. And what we did with this data set was go from, you know, this is the original Huff indexing. It's a phase map on the left, the orientation map on the right, and we've really built it up and kind of, you know, it's not like we're filling in the blanks entirely, but we've improved the data set a little bit more for better study. And so I've kind of been burying the lead the whole time, but, you know, we never got to the bottom of the tentpole solution here. And it's actually quite similar to the 304 that we were just looking at. But this is a case that was reprocessed. It was using the indexing, the DTM sweep, to solve the 0 solutions, to see if we can really, if there was something there that is valuable, and then doing the hybrid pattern matching using refinement and repair. And here's what the reanalysis gives us. I mean, it's a really good phase map on the left. We don't have that speckling that we kind of saw in the original data. If you look at the orientation map on the right, there's a lot more detail, especially in what seems to be kind of slip bands up in the upper portion of the image there. So gives us more detail to work with. If you look at a kernel average disorientation map, we've kind of, you know, really improved the resolution here, especially when you start to look at regions around these inclusions. And if you looked at it originally, the Huff indexing didn't give you much to work with, didn't give you it all the way to the boundary of the inclusion, didn't let you kind of analyze if that was where a crack initiation might have started. When you look at it with pattern matching, you have a lot more detail to work with there. I think that was ultimately the conclusion that was here is, conclusion was that the inclusions might have been causing the problem to begin with. But it's worth kind of noting the slip bands at the upper portion of the image that are starting to tell a story too that you can improve on with the map sweepers. So to put a bow on it, you know, we've introduced pattern matching. It has a number of benefits over the conventional Huff-based indexing, but by no means are we trying to replace it. It's meant to supplement it. It's meant to improve difficult samples here in a lot of ways. So the hybrid pattern matching we see is something that's time effective. something that realistically you could do with, you know, I hate to say every sample because I want you to think about why you're doing it before you do it. But it's something that's, you know, not going to be a high time issues. We also have kind of the brute force dynamic template matching to go with this. You're going to potentially need this on occasion, you know, but where we're trying to go, you know, improving angular precision, resolving pseudosymmetry, phase discrimination, you know, really trying to improve the data where we possibly can here. So you kind of saw with a lot of the examples here that, you know, it enables a little bit more research to be done, enables a little bit more material characterization than you might be possible with the original Huff indexing. So with that, I'll say thank you, and we can take questions real quick.
Great. Thanks so much, Mike, for the great talk. We have a few questions in the Q&A, but if anyone else has additional questions, please feel free to pop them in there now, and we can either answer them live or I'm sure Mike can follow up. So the first question is about lattice parameters and variation in lattice parameters in MapSweeper. And someone's wondering if it's possible, if there are any internal variations, if that can be detected with MapSweeper.
It's a good question. I think of it as a possibility. It really depends on, you're going to have to create a pattern simulation using, you know, specific lattice parameters. It's coming from a CIF file is what we use to generate the simulations. So I could envision a potential case where you might try two different patterns, but using them within the same map, I don't believe that that's something that's possible at the moment.
Okay, thank you. Someone else asked, why and how is hybrid pattern matching faster?
Okay, yeah, that's a good question, and maybe I failed to explain it really, really well in that case. Hybrid pattern matching is going to be faster simply because we're not creating as many simulated patterns. So we have this spherical, you know, simulation that we're creating to start with, but we're taking segments of it and projecting it into 2D. If we're going to do the dynamic template matching, it could be, you know, a large number of patterns that you're generating versus the refinement and the repair sweep, as I described, which is the hybrid matching, already has that Huff value. You already know where the orientation is roughly. So you're only creating maybe 100 or 200 patterns at most right around that orientation. It should just, you know, breeze through it real quick.
Nice, thank you. The next question was, how accurate is the hybrid pattern matching? And I'll sort of build on top of that. I'm wondering, so one of the things you mentioned is, you know, you get the high correlation coefficient with the elephant. And I'm wondering if there's any sort of way that as the user, you can sort of review certain things that were like newly indexed and say like, no, that doesn't really make sense for this particular sample, or is it all sort of black box?
Sure. So yeah, in terms of the accuracy, it's really that cross correlation factor that you should be using as a guideline for that. And it's almost like giving you some kind of confidence number. You know, we're still kind of trying to say, you know, here's a number that's really good. Here's a number that's maybe questionable. But like I said, you know, we'd like to see everything above 0.25 as a starting point. You have the option in the software to kind of say, this is the minimum R value that I'll accept. And it might default to, I think it defaults to 0.15. So if you kind of go, that's not good enough, just raise it up. And when you do the pattern, when we do the MapSweeper run, every pixel will generate some kind of R value that you could go back and replot as a map. So you could kind of focus in on regions where like, oh, you know, here the R factor was terrible. You could even subset based on that R factor and go in and do an analysis of what's gone on in that situation there. So yeah, there's a lot of potential to review the data a little bit more closely. Got it.
All right. Thank you so much for the nice talk, Mike and Ben. I don't see any more questions, so I think we'll wrap up. The recording of this webinar will be posted on Nuance's YouTube channel if anyone's interested in following up later. And thank you again to our great speakers. Have a good day, everyone.
Thank you, everyone.